Space is zero gravity. You've probably seen it in movies or on TV. Astronauts floating around inside their spaceships, spinning like Olympic gymnasts, tossing water bubbles that just hang in the air. And maybe you thought, wow, space must be zero gravity. There's literally no gravity up there. I mean, who wouldn't think that? The visuals are convincing, and the term zero gravity itself sounds super official. Like, gravity just disappears as soon as you leave Earth. Poof, gone. You're suddenly weightless, free-floating, and living the ultimate anti-gravity dream. Sounds amazing, right? But here's the thing. That's not actually how it works. Gravity doesn't magically turn off once you leave the ground. Nope. Gravity is everywhere, and that includes space. Even at the altitude of the International Space Station, about 250 miles above Earth, gravity is still roughly 90% as strong as it is on the surface. 90%. Yeah, you read that right. Gravity doesn't vanish just because you're off the planet. It's always there, tugging at everything. That's the universal rule. So, if gravity is still so strong up there, why do astronauts float around like they're in some zero-G playground? This is where the magic of free fall comes in. It's a little counterintuitive, but it's also really cool. The International Space Station, or any object in orbit, is actually falling toward Earth all the time. But here's the catch. It's moving sideways incredibly fast. Like, insanely fast. About 17,500 miles per hour. Because it's moving so quickly forward, as it falls, it keeps missing Earth. It's constantly falling, but it never hits the ground. That's what orbiting is. You're in a continuous state of free fall, and everything inside the station is falling at the same rate. That's why astronauts appear to float. They're not floating because there's no gravity. They're falling together with the station. Mind-blowing, right? To picture it better, imagine this. You're on a swing at the playground, but this is a magical swing. You swing so high and so fast that as you come down, the swing moves forward just enough that you never hit the ground. You just keep moving, falling, and circling endlessly. That's essentially what orbiting is. Or another way to think about it is, imagine running around a giant hill at full speed. You're always going downhill, but you never actually reach the bottom because your forward speed keeps you circling the hill. That's the orbiting dance Earth and its satellites are doing all the time. And while astronauts are floating inside the station, gravity is still very much present. It's tugging on them and on everything around them. Space station, water bottles, even tiny bits of dust. But because they're all falling together, they experience that weightless sensation. Imagine being in an elevator with the cables cut. You'd feel weightless for a few terrifying seconds. Now imagine that, but over and over for months at a time, except much safer and with life support systems. That's what astronauts live with every day. Here's another fun fact. The ISS completes a full orbit around Earth roughly every 90 minutes. That means astronauts get to see 16 sunrises and 16 sunsets every single day. Can you imagine trying to keep track of time with that? And yes, even though they're floating, they're technically falling around the planet at breakneck speeds. So when you see an astronaut tossing a water bubble and it floats in midair, it's not magic. It's just physics doing its thing. The bubble is falling at the same rate as the astronaut and everything else inside the station. Pretty neat, huh? Pop culture doesn't help the misunderstanding. Movies and cartoons love to exaggerate the zero-gravity thing. They show astronauts flipping around effortlessly, throwing objects and spinning in ways that make you think gravity simply doesn't exist in space. And honestly, I get it. These visuals are mesmerizing. But the truth is even cooler because it's real physics at work. Astronauts aren't defying gravity. They're showing us what free fall looks like on a massive scale. It's like the ultimate demonstration of orbital mechanics in action. And here's a thought. Wouldn't it be amazing if we could just step off our chairs and float around like astronauts? Yeah, but don't get too excited. Remember, in space, you're also falling at 17,500 miles per hour. Not exactly a casual stroll. So maybe stick to floating in a pool here on Earth. It's a lot safer, and while it's not exactly orbiting Earth, it still gives you a taste of that weightless sensation. So, next time you see astronauts drifting gracefully inside the space station or bouncing a water droplet across a room, remember this. Space is not zero gravity. Gravity is everywhere, tugging at you constantly, even hundreds of miles above Earth. Astronauts float because they, along with everything else inside their station, are in continuous freefall. It's falling without ever hitting the ground. And that's what orbiting is. In a way, it's kind of poetic. Gravity never lets go, but astronauts still get to live the ultimate floating experience. And now, you know the secret. It's all about falling. Together. Really, really fast. Around the planet. So, next time someone tells you space is zero gravity, you can smile and say, nope, gravity's everywhere. They're just falling in style. Astronauts can float anywhere in space. You've probably imagined it before. Leaving Earth, stepping out of your spaceship and just floating. Like drifting through space forever, weightless and free, with stars all around and no strings attached. Movies and cartoons make it look so easy. Astronauts tumbling around between planets, twirling near stars, even floating near black holes like it's some giant zero-gravity playground. And honestly, it looks amazing. Who wouldn't want to try it? But here's the truth, and it's a little more complicated than Hollywood would have you believe. Floating in space isn't some universal magic that happens everywhere. It only happens under very specific conditions. Mainly, astronauts float when they're in orbit or freefall, like inside the International Space Station. That's because both the station and everything inside it, including the astronauts, are falling around Earth at the same speed. They're not weightless because gravity vanished. They're falling together. And when you're falling together with something, you experience what feels like weightlessness. That's what makes astronauts appear to float. Now, here's where it gets interesting. Imagine you're way out in deep space, millions of miles from any planet or star. It might seem like you just drift forever, untethered, with nothing pulling on you. But the truth is, gravity is everywhere. Even in deep space, there's still a tiny pull from stars, planets, and galaxies. It's not enough to slam you into anything or pin you down like on Earth, but it's there, constant, inescapable. Gravity doesn't just switch off because you left the planet. That's a hard pill to swallow for anyone who grew up watching sci-fi zero-G adventures. To help picture this, think of a giant invisible web stretching across the universe. Every massive object, planets, stars, even entire galaxies, exerts a tiny tug on everything else.
Even if you were floating somewhere far from Earth, the sun would still pull on you. Nearby planets would tug, and the Milky Way itself would add its subtle nudge. It's like being a feather caught in a slow, gentle breeze that never stops, with invisible hands pulling you in every direction. You're floating, yes, but gravity is still there, gently tugging you along. And speaking of stars, even the Andromeda Galaxy, which is millions of light years away, exerts a tiny gravitational pull on you right now. You can't feel it, of course, and it doesn't really affect your day-to-day life, but it's happening. That's the mind-bending part about space. It's vast, empty, and seemingly weightless, but invisible forces are constantly at work. Gravity is everywhere, just quietly doing its thing, shaping the motion of everything in the universe. This also explains why floating isn't just drifting freely. Astronauts on the ISS float because they're falling with the station. Future astronauts traveling to Mars or beyond will float inside their ships because their spacecraft is in free fall around whatever gravity source they're near. But out in interplanetary space, away from planets or moons, you wouldn't just float like in a cartoon. You'd feel the faint pull of gravity from the sun, from Jupiter, from distant stars. It wouldn't pin you down, but it would subtly guide your trajectory. Space may look empty, but it's full of invisible tugs and nudges everywhere. Now let's bring this closer to home. You might be sitting in your chair right now thinking, well, I can't feel any gravity pulling me sideways, so this doesn't matter. But the reality is, you are constantly under the pull of gravity, Earth's gravity mainly, but also from the sun, the moon, and yes, even distant planets. The same principle applies in space, except the tugs are smaller and spread out over much larger distances. Floating anywhere in space isn't like turning off a switch. It's about finding that sweet spot where free fall occurs and everything around you falls together. Pop culture really perpetuates the myth of universal floating. Movies show astronauts tumbling freely anywhere in space, and it looks effortless and fun. But reality is much cooler. Floating isn't magic, it's physics. Free fall, orbital mechanics, and gravitational tugs are all at work, creating a unique experience that only happens under specific conditions. Astronauts aren't defying gravity, they're showing us what falling together in orbit feels like. And it's exhilarating, no doubt, but it's not unlimited. You can't just step off a planet anywhere and float forever. So the next time someone tells you astronauts float anywhere in space, you can smile and know the secret. Floating only happens when you're in free fall with something else. Space is huge and almost empty, but gravity is sneaky. It's everywhere, pulling on everything, even far away from Earth. Astronauts float because they're falling together with their spacecraft. In deep space, you might drift, but you're still under the subtle, invisible tug of gravity from countless stars, planets, and galaxies. It's like an invisible cosmic dance, and astronauts are lucky enough to be part of it. And honestly, that's kind of poetic, isn't it? Gravity never really lets go, yet astronauts still get to experience the ultimate floating adventure. It's a reminder that space is full of hidden forces, subtle movements, and mind-bending physics. Floating isn't zero gravity, it's falling in style. And now you know the secret behind the cosmic choreography. So the next time you imagine drifting among the stars, remember, gravity is always there, quietly guiding you, even when you can't feel it. That's what makes space so fascinating, mysterious, and endlessly fun to explore.
Planets have no gravity in space. You've probably heard it a million times, especially if you've spent any time watching sci-fi movies or space cartoons.
Someone will say, once you leave a planet, there's no gravity. You're weightless. And on the surface, that makes sense. You get on a spaceship, zoom off into the great unknown, and suddenly you feel nothing pulling you down. So it must mean gravity disappears entirely, right? Sorry to break it to you, but nope, that is totally false. Planets still have gravity, even in space. Now, I know what you're thinking. Wait, I don't feel it when I'm floating around in a spaceship. How can it still be there? Here's the thing. Gravity isn't just something you feel with your feet on the ground. Gravity is a force that every object with mass exerts. Every single object, from a tiny pebble to the sun itself, has it. The bigger the mass, the stronger the pull. That means planets, moons, stars, and even you, technically, have gravity. Yep, your backpack has gravity too. But don't get any ideas about starting a planet-sized fight over it. So why do we get confused about planets losing gravity in space? Well, part of it is movies again. Sci-fi shows and cartoons love to show astronauts tumbling freely around, drifting past planets like they're floating in a completely neutral void. In these fictional worlds, gravity seems to vanish as soon as you leave a planet's surface. And in a spaceship, you can't really feel the pull of the planet you just left because you're falling around it. That's why it looks like there's no gravity. But there really is. You're just falling along with your spacecraft. Think of it like surfing a wave. You're moving with the wave, so it doesn't push you down the way it would if you were standing still. Here's a really cool way to picture it. Imagine a magnet. You place it near a fridge door, and it sticks. Move it farther away, and the pull gets weaker, right? But it's still there. Gravity works the same way. The Earth is like that magnet, and you, your spaceship, or even a tiny asteroid are like the fridge door. Even far out in space, gravity's pull is still active. It's just weaker because distance reduces the strength of the force. So when astronauts float inside the International Space Station, which orbits about 250 miles above Earth, they're still under roughly 90% of the gravity they would feel on the ground. They're floating, not because gravity is gone, but because they are in free fall with the station. The planet is still pulling, they just don't feel the tug the way we feel it standing on solid ground. And it gets even crazier when we look at other planets. Jupiter, for example, is a colossal gas giant. Its mass is so huge that its gravity can reach millions of miles into space, tugging on comets and asteroids, and even influencing the orbits of moons that are far away. If you tried to fly past Jupiter thinking its gravity wouldn't touch you, think again. The planet would gently but persistently tug on your spaceship. And it's not just Jupiter. Even smaller planets and moons exert gravity. The moon's pull, though tiny compared to Earth's, is enough to control the tides here. You don't need to be standing on a planet's surface for gravity to exist. It's there regardless. Now let's step back a bit. Deep space might feel empty, like you're floating in nothingness. But the truth is that gravity is everywhere. There's a tiny pull from every planet, star, and galaxy. Even distant galaxies like Andromeda exert a minuscule tug on everything in the universe, including you right now. You can't feel it, of course, and it won't move you an inch, but it's still there. Gravity doesn't need a surface to cling to. It's a force that acts across space itself. So while floating around in a spaceship might make it feel like you're weightless, in reality, you're navigating a universe full of invisible tugs and pulls. This also explains why orbiting planets, moons, and satellites work the way they do. Satellites around Earth don't just float aimlessly. They're being pulled constantly by gravity. But because they're moving sideways fast enough, they never crash into Earth. They're in a delicate balance between their forward motion and the planet's pull, constantly falling around it. This is why astronauts in orbit float. They are literally falling together with their spacecraft. It's a cosmic dance orchestrated by gravity, and it works for every planet and moon in the universe, not just Earth. Gravity also affects interplanetary travel. Future astronauts traveling to Mars or beyond won't suddenly float freely in the void of space. They'll feel the gravity of planets, moons, and the sun, just much weaker than on Earth. Even tiny asteroids will pull on their spacecraft, subtly guiding its trajectory over long distances. Space may seem empty and weightless, but it's full of invisible tugs, guiding and shaping everything in it. So the next time someone tells you planets don't have gravity once you leave the surface, you can smile and know the truth. Planets always have gravity, whether you can feel it or not. Floating in a spaceship doesn't make it vanish. It just changes how you experience it. You're falling along with everything else, riding the invisible pole like a cosmic surfer, while the planet's gravity continues to extend far into space. In the end, gravity is relentless. It never takes a break, it never sleeps, and it never disappears. Planets, moons, stars, and galaxies, all of them are constantly pulling, shaping the universe, and guiding everything around them. Floating in space might look like weightlessness, but it's actually a masterclass in physics, a dance choreographed by gravity itself. Every mass matters, every pull counts, and every orbit is a demonstration of just how persistent gravity really is. So yeah, planets do have gravity in space. They never let go, and neither does the laws of physics. Floating around is just us experiencing it in the coolest, most mind-bending way possible. Next time you picture astronauts drifting around, remember, gravity is the invisible hand guiding the show. It's everywhere, it's constant, and it's the reason the universe doesn't just fall apart into a chaotic mess. Gravity might be invisible, but it's the ultimate cosmic organizer. And planets? Well, they're just flexing their gravitational muscles, whether you feel it or not.
Satellites just hover in place. You've probably looked up at the night sky and seen a tiny dot gliding smoothly across the darkness. Maybe you thought, wow, that satellite is just hanging there, silently keeping an eye on us, floating perfectly in place, like some celestial magic trick. Movies, cartoons, even school diagrams make it look like satellites just hover above Earth, fixed in the sky. And honestly, if you've ever stared at one moving slowly, it's easy to believe that they're completely stationary, just patiently doing their job, floating in midair like some cosmic ornament. Right? Well, not exactly. Satellites don't hover in space like magic, not even close. The truth is way cooler and way more mind-bending. Satellites are actually constantly falling toward Earth. Yes, you read that correctly. They're falling. But here's the trick. They're also moving sideways at incredible speeds, so fast that as they fall, they keep missing the planet.
This delicate balance between falling toward Earth and moving forward at high velocity is what creates orbit. Satellites aren't suspended in midair, they're in a continuous state of free fall, circling Earth forever. Let's break it down with a simple mental image. Imagine standing on a cliff and throwing a ball forward. Gravity will pull it down, and if you don't throw it far enough, it lands somewhere below. But what if you could throw it fast enough that as it falls, the curvature of the Earth drops away beneath it? You'd throw the ball, it would keep falling, but it would never hit the ground. It would keep circling the planet. That's essentially what a satellite does. It's a carefully aimed object in free fall with enough horizontal speed to orbit the planet instead of crashing. Mind-bending, right? Now let's visualize it another way. Picture a swing at a playground. Normally the swing goes back and forth, up and down, eventually stopping. But imagine a magical swing that keeps moving forward as it falls. You're always being pulled downward by gravity, but your forward motion keeps you moving in a circular path. That's what satellites do, except instead of a playground, they're hundreds of miles above Earth, moving at thousands of miles per hour. And unlike a swing, they don't slow down. They keep orbiting endlessly, performing a perfect cosmic dance. Here's a crazy fact. The International Space Station, one of the most famous satellites, orbits Earth at around 17,500 miles per hour. That's fast enough to complete a full orbit in just 90 minutes. Imagine seeing 16 sunrises and sunsets in a single day. And the astronauts inside aren't floating because gravity is gone. They're falling together with the station, moving forward so quickly that they never crash. It's free fall on a planetary scale. And it's not just the ISS. Every satellite up there, whether it's a GPS satellite, a weather satellite, or a communication satellite, is doing the same thing. They're all falling constantly, but their incredible speed keeps them in orbit. It's a delicate balance, like a cosmic tightrope walk. If they go too slow, they'd plummet to Earth. Too fast, and they could escape Earth's gravity entirely and drift off into space. Orbiting is all about balance, gravity pulling in, speed pushing out, and satellites are perfect examples of physics in action. You might be wondering, so why do they look like they're hovering when I see them in the sky? That's a matter of perspective. From the ground, satellites seem to move slowly because they're so far away, even though they're moving at mind-blowing speeds. It's the same illusion you get when a plane looks like it's crawling across the horizon, even though it's flying hundreds of miles per hour. Distance compresses perception, making satellites appear stationary, or at least leisurely drifting, when in reality, they're falling around Earth in a high-speed orbital ballet. Even geostationary satellites, the ones that seem to hover above the same spot on Earth, are still orbiting. They just orbit at a specific altitude, about 22,236 miles above Earth, where their orbital period matches Earth's rotation. So from our perspective on the ground, they appear fixed, but in reality, they're moving, falling, and orbiting, just like every other satellite. It's all about timing and speed. They're balancing gravity perfectly so that they circle Earth in sync with its rotation. It's like running on a treadmill that's rotating beneath you. You stay in the same spot relative to the treadmill, but you're still moving fast enough to keep up. Now, let's be honest for a second. Satellites floating in the sky like magic is a beautiful misconception.
It makes space feel calm and orderly, like a still painting in the night sky. But the reality is far more impressive. These satellites are performing an endless, high-speed dance around Earth, constantly falling, constantly moving, perfectly choreographed by gravity. No strings, no magic, just pure physics at work. And that's what makes orbiting so amazing. Seeing weightless movement in action guided entirely by the invisible hand of gravity. So, next time you spot a satellite gliding across the night sky, remember this. It's not hovering like some celestial ornament. It's falling around Earth at insane speeds, balancing gravity perfectly to stay in orbit. What looks like stationary magic is actually one of the coolest examples of physics in the universe. Orbiting is falling without hitting the ground, and satellites are masters of that fall. It's a cosmic dance you can't feel from the ground, but now you can picture it clearly. Gravity never takes a day off, and neither do satellites. They're falling, gliding and orbiting in a delicate balance that keeps our modern world connected, our weather forecasted, and our GPS maps working. Floating in space may seem effortless from the ground, but it's really physics performing one of its most elegant routines. So remember, satellites don't hover. They fall beautifully, endlessly, and at breathtaking speeds. And that's the real story behind the magic in the night sky.
You cannot escape gravity instantly. You've probably seen it 100 times in movies or TV shows. Rockets blast off, fire blazing, smoke everywhere, and suddenly they're in space. Astronauts float weightlessly, gravity is gone, and they drift among the stars. One moment they're grounded, the next they're effortlessly floating like magic. And if you're like most people, you might think, wow, leaving Earth is as easy as pushing a button or stepping off a cliff. Gravity? Gone in an instant. Easy as pie. Sounds amazing, right? Well, here's the truth, and it's a lot more fascinating than Hollywood would have you believe. You cannot escape gravity instantly. Gravity doesn't just switch off the moment you leave Earth. It's not like stepping on a ladder and suddenly stepping into a zero-G zone. Gravity is always there, tugging at you, pulling you back. Reaching orbit isn't just blasting straight up into the sky and hoping for the best. It's a delicate dance, a careful balance of speed, angle, and trajectory. Let's break it down with a simple example. Imagine throwing a ball straight up. What happens? It goes up, slows down, stops for a split second at the top, and then falls right back down. That's gravity doing its thing. Now, imagine throwing that same ball sideways while also throwing it up. If you throw it fast enough, the ball starts moving forward so quickly that as it falls, it never hits the ground. Instead, it keeps circling, following the curve of the Earth. That's basically what orbit is. A rocket doesn't just go straight up. It also has to go sideways at incredible speed, constantly falling around the planet without crashing. That sideways motion is critical. It's the secret ingredient that makes orbit possible. And the speeds involved are mind-boggling. To orbit Earth, a spacecraft needs to reach about 17,500 miles per hour, roughly 5 miles per second. That's faster than any car, plane, or anything you've ever imagined moving on Earth. And it's not enough to just reach that speed. The rocket has to follow a precise path. Too slow, and it falls back down. Too fast, and it could escape Earth's gravity completely, drifting off into deep space. It's a cosmic tightrope act where every mile per hour counts.
Even the early moments of a rocket launch are all about fighting gravity. The first stage of a launch is basically a battle. The rocket engines have to produce enough thrust to overcome Earth's gravitational pull while also accelerating sideways to reach orbital velocity. The astronauts aren't just blasting off into free-floating magic, they're climbing a hill that never ends, constantly battling the pull of a massive planet. And it takes minutes, not seconds, to reach orbit. The Apollo missions to the moon didn't escape Earth instantly. They climbed slowly, carefully, balancing speed, trajectory, and engine power to get into orbit safely. Let's visualize this another way. Think of a skateboarder trying to skate perfectly along a curved halfpipe. If they go too slow or approach at the wrong angle, they wipe out. Go too fast and they fly over the edge. But if they hit the sweet spot, they glide smoothly, looping perfectly. That's what rockets do when reaching orbit. Gravity is like the walls of the halfpipe, constantly pulling, and the rocket has to move at just the right speed and angle to stay in the orbiting path. Every maneuver, every thrust is a careful calculation. Even after reaching orbit, gravity never goes away. Astronauts floating inside the International Space Station aren't weightless because gravity disappeared. They're falling together with the station. It's free fall on a massive scale, not an escape from gravity. And that free fall is precisely why orbiting feels magical. The sensation of floating isn't gravity-free, it's falling at the same rate as everything around you, perfectly synchronized in a delicate cosmic ballet. And here's a fun fact. Even if a rocket goes perfectly straight up at insane speed, it won't automatically stay in orbit. It might escape Earth's gravity entirely, but then it's on a trajectory into deep space, not orbiting Earth. Orbit isn't about getting far from the planet, it's about moving sideways fast enough that you fall around it, not away from it. It's about balance, speed, and direction, all working together to counteract gravity without escaping it completely. So, the next time you see a rocket launch or watch astronauts floating in orbit, remember this: there's no instant escape from gravity. Reaching orbit is a carefully choreographed dance of physics, with gravity constantly pulling, engines pushing, and speed perfectly balanced. Floating in space isn't something you do instantly. It's something you earn by navigating the invisible force that has held everything together since the beginning of the universe. Gravity never takes a day off. It's always there, silently tugging at everything from tiny pebbles to massive planets. Rockets don't magically leave it behind. They work with it, carefully, strategically, and with incredible precision. And that's the beauty of reaching orbit. It's not a sudden miracle, it's a brilliant demonstration of physics, engineering, and human ingenuity working together. So, yes, leaving Earth is amazing. Floating in space is breathtaking. But it's not instant. It's earned. It's precise, and it's the result of understanding the delicate balance between gravity, speed, and trajectory. Rockets don't escape gravity. They embrace it, dance with it, and use it to stay in orbit. That's the real magic behind the scenes, far cooler than anything Hollywood could show.
The sun is yellow. You've probably seen it countless times. Pictures, textbooks, cartoons, even your classic sunshine emoji. Everywhere the sun is painted as bright yellow, golden, glowing, and warming everything in sight. And if you've ever looked up at the sky yourself, especially during early morning or late afternoon, it does sometimes look yellow, right? So naturally, you'd assume the sun is, well, yellow. It seems obvious. But here's a secret. The sun isn't yellow at all. Not even close. In reality, the sun is white, a dazzling, pure white ball of light. And the yellow we see is mostly a trick played by our atmosphere. Now, I know what you're thinking. Wait, hold on. Every picture I've ever seen shows it yellow. You're telling me that's wrong? Yes, exactly. And the reason we've believed this for so long is pretty simple. Human perspective and Earth's atmosphere. Movies, cartoons, textbooks, and even art love to paint the sun as yellow. It's visually striking and immediately recognizable. And, well, sometimes it does look yellow when it rises or setting. Combine that with centuries of artistic convention, and it's no wonder everyone thinks the sun is yellow. But let's dive into the science. The sun actually emits white light, which is essentially a combination of all the colors in the visible spectrum. That includes red, orange, yellow, green, blue, indigo, and violet. Everything mixed together. If you could float in space, right next to the sun but far enough to survive, you wouldn't see yellow. You'd see a bright, intense white star, dazzling enough to make you squint or shield your eyes. It's not the soft, mellow yellow we're used to seeing in cartoons. It's pure, glaring white light, the sun in its natural form. So why do we see it as yellow from Earth? That's where atmospheric scattering comes in. Earth's atmosphere is full of tiny particles and gases, which scatter sunlight. Blue and violet light, the shorter wavelengths, scatter more than the longer wavelengths like red, orange, and yellow. This scattering is why the sky looks blue most of the day and why the sun seems more yellow, orange, or even red when it's closer to the horizon. During sunrise or sunset, sunlight has to travel through more of the atmosphere, scattering even more of the blue and leaving behind those warmer golden tones we're familiar with. Basically, Earth's atmosphere is a giant color filter, giving the sun its yellow appearance. Think of it like this. Imagine shining a white flashlight through fog or smoke. The light coming out doesn't look exactly the same. It gets filtered, scattered, and diffused. That's what our atmosphere does to sunlight. From space, with no atmosphere to scatter light, the sun doesn't change color. It remains that brilliant white star we mentioned earlier. Astronauts aboard the International Space Station see the sun this way every day, blazing white against the black void of space, completely untouched by Earth's atmospheric tricks. And here's another fun twist. Even the term yellow dwarf, which is a common nickname for the sun, can be misleading. Astronomers use it as a classification for a G-type main sequence star based on its temperature and spectrum, not the actual color you see with your eyes. So the sun is called a yellow dwarf, but if you floated in space, you'd see it shining white, not yellow. It's one of those moments where scientific jargon doesn't quite match everyday perception, and it's a great example of why context matters when learning about space. And the story gets even more interesting when you think about other planets. Sunlight looks different depending on the atmosphere you're looking through. On Mars, with its dusty, thin atmosphere, the sun can appear more reddish or orange. On Earth, it's yellow through most of the day. In space, it's white. The color we perceive isn't just about the sun itself. It's about where we're standing and what we're looking through. Our atmosphere is like a painter, adding warm hues to the sun's natural white light. So next time someone tells you, the sun is yellow, you can nod politely and think, not exactly, That's just Earth's atmosphere having fun with the sun's color. The truth is cooler, even more dazzling, and a little mind-bending. Floating in space, the sun doesn't conform to our expectations. It doesn't change just because we want it to be yellow. It's a blinding, brilliant white star shining across the cosmos in all its unfiltered glory. And let's be honest, it's kind of poetic. The sun is a giant ball of white light, constantly emitting energy, constantly sustaining life on Earth, and yet we perceive it as golden, orange, red, simply because we're looking at it through our atmosphere. It's a beautiful reminder that our perspective shapes what we see, even in something as universal and seemingly obvious as the sun. So the next time you see pictures of the sun or watch a cartoon with a yellow circle in the sky, remember this: the sun isn't really yellow. It's white. The yellow you see is Earth's atmosphere playing tricks on your eyes, scattering light and adding warm tones. Step outside at sunrise or sunset, and you'll notice the effect more dramatically. Fly in space, and you'd see the raw, dazzling white brilliance of our nearest star. Either way, it's a reminder that space is full of surprises, and things are often not what they seem. In the end, the sun isn't just a yellow ball in the sky. It's a giant cosmic powerhouse, a white star radiating light in all directions. Yellow is just Earth's version of the sun, a filtered, atmospheric rendition of what's truly out there in space. And once you know the truth, every sunrise, sunset, and space picture becomes a little more fascinating, because now you see the sun and the invisible hand of Earth's atmosphere at work.
Stars twinkle in space. Look up at the night sky on a clear evening, and you're bound to notice it. Thousands of stars sprinkled across the darkness, glittering, sparkling, twinkling like someone just shook a giant cosmic bottle of glitter. It's mesmerizing, beautiful, even magical. Twinkle, twinkle, little star. It's like the universe itself decided to put on a nightly light show just for us. Movies, storybooks, and even science diagrams reinforce this idea. Stars twinkle. It's so familiar that most of us assume stars naturally flicker, shimmer, and change color in space. But here's the truth. Stars only twinkle because of Earth's atmosphere. Yep, that's right. Twinkling isn't a property of the stars themselves. It's a side effect of looking at them from inside the layers of air surrounding our planet. When starlight travels through our atmosphere, it passes through pockets of air that are constantly moving, warming, cooling, and shifting. This turbulence bends and refracts the light in slightly different directions, making it appear as if the star is flickering or dancing. It can even change color moment to moment because shorter wavelengths like blue and violet scatter more than red and yellow. The twinkle is not the star showing off. It's Earth giving you a nightly light performance for free. Think of it like looking at a street lamp through a window on a hot summer day. You know that wavy, shimmering effect? That's caused by heat rising and distorting the air. Suddenly, the lamp seems to flicker, jump, or dance. That's exactly what happens with starlight, only on a much larger scale and with some very distant light. Or imagine seeing a laser pointer through rippling water. Steady light becomes wobbly and uneven. That's your atmosphere at work, turning a steady point of light into something that seems alive. Now contrast that with space. Step outside Earth's atmosphere, like astronauts on the International Space Station do, and those twinkling stars suddenly stop. No flickers, no shimmering, no shifting colors, just pure, steady, dazzling points of light stretching across the void. Stars in space are like lasers or high-definition light bulbs, precise, constant, and unwavering.
The twinkle disappears completely because there's no moving air to bend the light. The stars themselves haven't changed. It's simply that we're no longer looking through Earth's turbulent lens. Astronomers have known this for a long time, which is why so many telescopes are either placed in space, like the Hubble Space Telescope, or equipped with adaptive optics. Adaptive optics are amazing little systems that compensate for atmospheric distortion in real time, adjusting the telescope's mirrors hundreds of times per second to make stars appear sharp and stable. On Earth, it's basically like giving your telescope corrective glasses to untwinkle the stars. Space telescopes, of course, don't need them. They're already above the atmosphere, seeing stars in their true, steady glory. And here's another cool tidbit. Twinkling can also affect perceived color. On Earth, a star might appear blue one moment, red the next, just because of how the atmosphere bends different wavelengths differently. Remove the atmosphere, and the star's true color emerges. Some stars that look white, yellow, or slightly red from Earth are actually very different in their true light. Astronauts and space telescopes see them exactly as they are, without any flicker or filter, revealing a side of the universe that we can only imagine from down here. It's easy to see why the myth persists, though. Twinkling is so common and visible that we naturally assume it's part of what stars do. For centuries, humans have observed the night sky, noticed the sparkle, and told stories about it. The stars are dancing. The stars are alive. The stars are watching us, we say. And in a poetic sense, that's true, but only from our vantage point on Earth. Step outside our atmosphere, and stars are calm, steady, and constant. A true cosmic reveal, a universe in high definition. So the next time you gaze up at twinkling stars, remember this. They're not showing off. The sparkling you see is Earth's atmosphere bending and shifting their light, giving us a nightly visual treat. It's a subtle reminder of how our planet shapes our perception of the universe, even when the objects themselves are light years away. It's almost like we're seeing a filtered version of reality, a little theatrical version of what's really out there. And isn't that kind of magical in itself? We get a free, shimmering light show every night just because we're standing under the sky. Yet space holds an even more profound truth. Remove the atmosphere, and the universe is calmer, sharper, and even more majestic. Stars shine steadily, perfectly aligned with the laws of physics, their brilliance uninterrupted by our chaotic air. The twinkle is just a gentle reminder that what we see isn't always exactly what is. Perspective, distance, and environment play huge roles in shaping our experience of the cosmos. So yes, stars twinkle, but only from Earth. Out there in the void of space, they're steady, unwavering beacons of light glowing with consistency and clarity that we rarely get to witness directly. The twinkle is Earth's atmospheric magic, a nightly performance we can enjoy from our little blue planet. And that's what makes stargazing so fascinating. One moment, you're enjoying the glittering, twinkling spectacle. The next, you know that out there, beyond the atmosphere, the stars are shining just as they always have, silent and perfect, waiting for us to reach the stars ourselves.
Supernovae are loud explosions. When you hear the word supernova, your brain probably instantly jumps to one image: a massive star exploding in a burst of fire, energy, and chaos. Movies and TV shows love this idea. There's always that dramatic moment. The screen shakes. The sound effects thump, rumble, and boom. Epic orchestral music swells. You can almost feel the shockwave knocking over planets in your imagination. It's Hollywood at its finest, right? The universe's grandest fireworks show, complete with thunderous sound. Well, here's the kicker. Space is completely silent. That's right. No booms, no rumbles, no crackles.
Supernovae, as spectacular and violent as they are, make no sound in space. And it's not a matter of them being far away. Even if you were right next to one, it would still be silent. You might ask, well, wait, but explosions are always loud. How can the universe ignore the rules of sound? The truth is that sound isn't magic. It's a wave that needs a medium to travel through. On Earth, when something explodes, it pushes air molecules around, compressing them into waves that reach your ears. That's sound. In water, it's the same principle, but with water molecules. But in the vacuum of space, there are no molecules to compress, no medium to transmit sound waves, just nothing. Pure, eerie silence. So what actually happens in a supernova? Instead of a loud bang, a star reaching the end of its life violently ejects its outer layers into space, releasing an incredible amount of energy in the form of light, X-rays, gamma rays, and matter. It's like the ultimate fireworks display, but all the fireworks are invisible to your ears. Light and particles travel outwards at insane speeds, tearing through the surrounding space. But it's all done in silence. You could theoretically sit there watching one of the universe's most powerful events unfold, and your ears would be blissfully unaware. No sound, just brilliance. To visualize this, imagine popping a balloon inside a vacuum chamber. In the open air, you'd hear a sharp pop. Inside the vacuum chamber, though, you see the balloon explode, fragments flying everywhere, but eerily, it's completely silent. That's exactly what a supernova is like, just on a cosmic scale. Or picture fireworks in a soundproof room. You see the sparks, the colors, the trails of light, but your ears register nothing. It's all visual drama, no auditory drama. And yet, supernovae are far from subtle. These explosions release more energy in a single moment than our sun will produce in its entire 10 billion-year lifetime. It's almost unimaginable. A single star ejecting massive amounts of matter at thousands of miles per second, forming nebulae, shock waves, and even seeding future stars with elements. Carbon, oxygen, iron, all the building blocks of planets and life are forged in these explosions, and all of this happens silently. The universe really knows how to make an entrance without using sound. Now, here's a fun twist. Astronomers can actually convert certain signals from supernovae into sound artificially. Instruments can measure plasma vibrations, electromagnetic waves, or radio emissions from supernova remnants and translate them into sound waves we can hear. But this is just data interpretation. It's not the star actually screaming. In space itself, even the mightiest explosion is mute. It's easy to see why the misconception exists, though. Back on Earth, every large explosion, volcanoes, bombs, fireworks, comes with a loud, unmistakable sound. We equate violence with noise. Movies, documentaries, and video games lean into this instinct, giving every cosmic explosion a booming soundtrack. So naturally, we assume a supernova would be deafening, but the universe plays by different rules, and space itself refuses to carry sound. Think about it. The silence of space makes these massive, violent events even more incredible. You can watch a star collapse, release energy equivalent to billions of nuclear bombs, and all you get is an awe-inspiring, blinding light show. The drama is in the motion, energy, and visual spectacle, not in noise. The universe is theatrical, but it's also eerily quiet.
a cosmic paradox of epic scale. And this silence extends to every part of space. Black holes devouring matter? Silent. Colliding galaxies? Silent. Even our own sun's solar flares? Silent. Unless they interact with Earth's magnetic field, creating auroras. Sound, as we know it, is entirely an earthly experience. Space is a stage where the rules are different. Motion, light, and gravity dominate. Air and sound waves do not exist. So next time you watch a star explode in a movie with all that rumbling, crashing, and booming, take a moment to appreciate the truth. Space is silent. All the sound effects are imagination, added for drama. Real supernovae are silent. Massive, brilliant, silent cosmic events that send light and matter hurtling across space, shaping the universe and seething future stars and planets, but without a single decibel. Silence doesn't make these events any less dramatic. On the contrary, it makes them even more mysterious. The thought that an event so powerful, so violent, and so important for life itself could unfold with zero sound is almost poetic. Space is a theater without a soundtrack, and supernovae are the grandest visual performance of all. So remember, supernovae are not loud explosions. They are powerful, brilliant, silent cosmic events, sending light and matter hurtling across space, shaping the universe and seeding future stars and planets, but without a single decibel. Silence doesn't make these events any less dramatic. On the contrary, it makes them even more mysterious.
Black holes suck everything nearby. Black holes. Just saying the words makes your imagination go wild. Massive, invisible, mysterious, and, yes, terrifying. Pop culture has done its best to paint them as cosmic vacuum cleaners, pulling in everything that comes too close. You've probably seen it in movies. A spaceship flies near a black hole, alarms blare, metal bends, and before you know it, whoosh, everything is gone, sucked into a dark abyss. Planets, stars, entire galaxies. Gone. End of story. Scary, right? But here's the twist. Black holes don't actually suck up everything nearby. Not even close. That dramatic, galaxy-sweeping vacuum cleaner image is mostly Hollywood imagination. Black holes are powerful, yes, with gravity strong enough to warp space and time. But they behave like any other massive object, just on a cosmic extreme. The key is distance. If something is far enough away, it orbits safely, just like the Earth orbits the Sun. You're not automatically doomed just by being in the same galaxy. Let's break it down with an analogy. Picture a whirlpool in a river. Toss a stick into the center, and it gets pulled under in seconds. That's the danger zone, the point of no return. But toss the stick a few meters away, it floats along the current safely, perhaps circling the whirlpool without ever getting sucked in. That's essentially how black holes work. Anything venturing too close, the so-called event horizon, gets trapped. Everything else, it dances around safely, orbiting the black hole in a silent cosmic waltz. Think about gravity for a moment. We know the sun is massive, right? Its gravity keeps planets, comets, and asteroids orbiting predictably. The same principle applies to black holes. They just have an extreme version of that gravity because of their density and mass. A star a few light years away from a black hole doesn't feel an immediate vacuum-sucking force. It orbits, interacts with other objects, and continues existing without being eaten. Even light itself can orbit a black hole at a specific distance, forming what astronomers call a photon sphere. Imagine light trapped in a cosmic racetrack, racing around a black hole endlessly, without actually falling in. That's as close to a black hole grabbing something as faraway objects can get, and it's mesmerizing. Another way to picture it, think about a strong magnet. Place tiny paper clips right on the surface, and they stick instantly. Move a few feet away, nothing happens. You're perfectly safe. The magnet has limits, even if it's powerful. Black holes are the same. Intensely strong, yes, but they don't reach across the universe and yank everything in. Gravity falls off with distance, and unless you're in that close danger zone, you're free to orbit, just like planets around a star. Let's address the drama factor in movies for a second. It makes sense why black holes are portrayed as universal vacuum cleaners. Explosions, collapsing stars, and inevitable doom make for fantastic visuals. They're terrifying, awe-inspiring, and perfect for storytelling. But in reality, the universe isn't quite so theatrical. Stars orbit black holes for millions, even billions of years without ever getting pulled in. Some black holes at the center of galaxies host entire systems of stars gracefully moving around them, like dancers in a cosmic ballroom. Far from chaotic destruction, these orbits are elegant, predictable, and surprisingly safe. Even when objects do get too close, there's a specific point called the event horizon, the ultimate point of no return. Cross that line, and gravity is so extreme that not even light can escape. That's the point where the black hole's reputation as a cosmic vacuum cleaner comes from. But here's the thing. The event horizon is tiny compared to the size of space around it. Most stars, planets, and galaxies never cross that line. The universe is vast, and black holes, no matter how powerful, don't have the reach to gobble up everything nearby. And here's something even cooler. Black holes are part of the cosmic ecosystem. When matter falls in, it doesn't just vanish without a trace. Sometimes it forms accretion disks, glowing with intense radiation, or is ejected in the form of jets at near-light speeds. These processes can influence nearby star formation and galactic evolution, showing that black holes aren't just destructive, they're also creative, shaping the universe around them. But none of this means everything gets sucked in instantly. It's a matter of proximity, speed, and trajectory. So next time someone panics about black holes sucking up everything nearby, you can smile and set the record straight. Black holes are insanely powerful, yes, warping space and time in mind-bending ways. They are extreme, mysterious, and awe-inspiring. But they don't indiscriminately devour everything around them. Only objects that stray too close cross the event horizon and become part of the black hole itself. Everything else? Orbiting safely, dancing silently, gracefully, in one of the universe's most mysterious and mesmerizing dances. It's terrifying, elegant, and absolutely mind-blowing, all at the same time.
Neutron stars are tiny pinpoints. When you look up at the night sky, stars appear as little dots, tiny, distant, twinkling lights far away in the vastness of space. Most of the time, we picture them as massive glowing balls like our sun, sure, but still relatively ordinary. Now imagine someone tells you that one of those tiny dots is actually insanely powerful, unbelievably dense, and capable of crushing cities with just a teaspoonful of its material. Sounds like science fiction, right? But that's exactly what a neutron star is. At first glance, neutron stars might seem insignificant. They're small, roughly the size of a city, around 20 kilometers in diameter. That's tiny compared to the sun, which is over 1 million kilometers across.
It's so small, in fact, that you could fit hundreds of neutron stars inside the volume of our sun. And yet, this tiny dot packs more mass than our sun. Mind officially blown yet? This is where the universe starts playing with extremes, bending reality in ways that our brains struggle to grasp. So why is it so dense? Neutron stars are born from the death of massive stars. When a massive star runs out of fuel, it explodes as a supernova, leaving behind a core that collapses under its own gravity. All the material that used to be spread out in the star's outer layers is squashed into a tiny, city-sized sphere. Imagine compressing the sun or even an entire Mount Everest into a sugar cube-sized object. That's the level of density we're talking about. 1 teaspoon of neutron star material would weigh billions of tons on Earth. Your teaspoon filled with this cosmic matter could flatten a city or a continent, depending on your imagination. To put it in a more relatable perspective, think about holding a teaspoon. Normally, a teaspoonful of sugar or salt is nothing, maybe a few grams. Now imagine replacing that sugar with neutron star material. Suddenly, your teaspoon is heavier than any building on Earth, heavier than Mount Everest, heavier than almost anything you can physically imagine. Your mind might want to protest, and that's fair. This is not normal physics. But the universe isn't normal. Neutron stars are extreme in every way, and they exist to remind us that size doesn't always equal weakness. And that's not all. Neutron stars also spin insanely fast. Some rotate hundreds of times per second. These are called pulsars, and they emit beams of radiation like cosmic lighthouses, sweeping across space with unbelievable precision. If you were close enough to see one, it would appear as a blinking light, but in reality, it's a tiny spinning city-sized star shooting beams of energy across thousands of light years. It's a visual and physical paradox, tiny yet immensely powerful, small yet extreme, simple yet completely mind-boggling. The gravity on a neutron star is another story. Standing on its surface is pure science fiction horror. The gravity is so intense that if you dropped a marshmallow on it, the sweet treat would hit the surface at about half the speed of light. Any human or any object not moving at cosmic speeds would be instantly crushed. Even light can be bent by the gravity, distorting space around the star. That tiny dot in the sky is a miniature powerhouse of gravity, density, and physics that defy everyday intuition. Neutron stars also show us the extremes of matter. The core is essentially neutrons packed together so tightly that they form a super-dense material called neutron-degenerate matter. It's one of the strangest states of matter in the universe, and it exists nowhere else that we know of. Your everyday experiences with solids, liquids, and gases give you no frame of reference for this. A teaspoonful weighs billions of tons. A city-sized sphere contains more mass than our sun. And yet, in the night sky, it looks like a tiny, twinkling point of light. It's tiny, yes, but don't let its size fool you. Neutron stars are cosmic extremes, the universe's way of proving that density, gravity, and power aren't about size. They're about the sheer intensity of matter and physics. In the end, neutron stars are a brilliant reminder that the universe operates on rules far beyond our daily experience. Small can be heavy, light can be intense, and tiny dots can hide unimaginable power. A teaspoon of neutron star material is billions of tons heavy. A city-sized sphere holds more mass than our sun. And yet, it all appears as a faint pinprick in the night sky. It's tiny, yes, but powerful, extreme, and utterly mind-blowing. Cosmic irony at its finest. Mercury is the hottest planet. When you think about the planets in our solar system, there's one common assumption almost everyone makes. Mercury is the hottest planet. I mean, come on. Mercury is the closest planet to the sun. It's practically sunbathing 24/7. Easy math, right? Close to the sun, a hotter surface. Makes sense. Mercury must be scorching, right? Well, not exactly. Not even close. In fact, the real champion of heat in our solar system is Venus, Mercury's slightly more distant sibling. And the reason might just blow your mind. Let's start with Mercury. Sure, it's the closest planet to the sun, and during its daytime, the surface can reach over 430 degrees Celsius. That's hot enough to melt lead. Sounds terrifying, right? But here's the catch. Mercury has almost no atmosphere. None. Zip. What does that mean? Well, without a thick blanket of air to trap heat, Mercury's surface heats up fast in the day, but cools down just as fast at night. When the sun sets, temperatures plummet to around minus 180 degrees Celsius. So while it's a scorching desert during the day, it's an icy wasteland at night. Mercury is a planet of extremes, swinging wildly between searing heat and freezing cold. Now, enter Venus. Venus is further from the sun than Mercury, so by that simple closer equals hotter logic, it should be cooler, right? Wrong. Venus is the hottest planet in our solar system, with surface temperatures averaging around 465 degrees Celsius, hotter than Mercury, even though it's farther away. How is that possible? The secret is Venus's thick atmosphere, a dense, choking layer of carbon dioxide that traps heat in a runaway greenhouse effect. Imagine wrapping the entire planet in a heavy, heat-retaining blanket that never lets go. The heat builds up, bounces around, and nothing escapes. Mercury might be closer to the sun, but Venus refuses to let any heat go. Picture this in everyday terms. Mercury is like standing in the desert, blazing hot under the sun, freezing cold in the shade. Venus, on the other hand, is like stepping into a pressure cooker that's been running nonstop for millions of years. No relief, no escape. You're stuck in a sauna that never cools down, day or night. Even if Venus were a little farther from the sun, that thick atmosphere keeps it hotter than Mercury every single day. Proximity alone doesn't determine planetary heat. Atmosphere does. And Venus's atmosphere isn't just thick, it's hostile. The clouds above the surface are made of sulfuric acid, raining down a toxic mist. The pressure on Venus's surface is about 92 times that of Earth, enough to crush most spacecraft like aluminum cans. So not only is Venus hotter than Mercury, but it's also far more deadly. A human visiting Mercury might freeze or roast depending on the time of day, but a human on Venus would be crushed and boiled instantly. Mercury is extreme, yes, but Venus is downright apocalyptic. Here's another fun fact. The thick clouds of Venus actually reflect sunlight, making Venus one of the brightest objects in our sky. You might look up at Venus and think, hey, that looks shiny and bright. Must be friendly. Nope, that brightness is just a surface reflection through toxic clouds hiding an oven hotter than any desert on Earth.
It's like a deceptive shimmer over a massive inferno.
So, why do so many people get this wrong? It's all about assumptions and simplifications. Mercury is closer to the sun, so our brains shortcut the logic. Closer equals hotter. Movies, cartoons, textbooks, they often repeat this, making Mercury seem like the ultimate scorcher. But reality is always more complicated. Venus reminds us that planetary climates are shaped not just by sunlight, but also by atmospheres, greenhouse effects, and chemical composition. Distance from the sun is just one piece of the puzzle. Now, imagine standing on Venus, or this thought experiment, since no human has ever survived there. The temperature would instantly melt lead. The pressure would crush your body. The air is toxic, poisonous, and filled with corrosive acid droplets. And all this heat comes not from being closest to the sun, but from the planet itself refusing to let any heat escape. Mercury might be a sunbather, basking under the sun for a few hours before cooling off, but Venus is relentless, a planetary oven that never lets go. In a way, Venus is a cosmic lesson about assumptions. Just because something seems obvious, like Mercury being the hottest planet, doesn't mean it's true. The universe loves to surprise us, bending logic, physics, and intuition in ways that make our brains spin. Venus's extreme heat shows that atmosphere, chemical composition, and climate systems matter far more than proximity alone. Mercury gets credit for being closest to the sun, but Venus deserves the crown for heat. It's a sauna on a planetary scale, a reminder that appearances can be deceiving. So next time someone confidently claims Mercury is the hottest planet, you can smile, shake your head, and say, actually, Venus takes the prize. Mercury might be small, sun-baked, and extreme in its own way, but Venus is a planetary inferno, relentless, unforgiving, and hotter than any planet in our solar system. Proximity doesn't always determine heat. Venus proves it with style, fire, and a thick, toxic atmosphere that traps the sun's energy like a cosmic pressure cooker. And there you have it. Mercury is close, yes, but Venus is the real heat champion. Hotter, deadlier, and far more extreme. A planet that shows the universe doesn't play by simple rules. The distance from the sun isn't the only factor, and that a thick atmosphere can turn a planet into a blazing, unescapable oven. Venus might be Venus might be small, rocky, and second in line from the sun, but when it comes to heat, it's number one.
Pluto is still considered a planet. Pluto. Just saying the name probably brings back a flood of memories. Classroom charts, planet songs, maybe even your pride in memorizing the order of the planets. Mercury, Venus, Earth, all the way to Pluto. That tiny icy dot at the far edge of our solar system. For decades, Pluto held a special place as the 9th planet, the underdog, the little world at the edge of the sun's kingdom. People loved Pluto, defended Pluto, and proudly called it a planet. And then, science hit us with a cosmic plot twist. Pluto is no longer officially a planet. Let's rewind a bit. Pluto was discovered in 1930 by Clyde Tombaugh, and at the time, it was immediately classified as the 9th planet. It was small, icy, and distant, but it fit neatly into the solar system lineup. Schools, textbooks, songs, everything reinforced that Pluto was part of the official planetary family. For decades, that was the rule, and generations of students learned to love Pluto as the final, mysterious world on the edge of the sun's influence. Then came 2006, And with it, the International Astronomical Union, or IAU, has the planet police decided it was time to define exactly what a planet is. The definition they created is simple, but strict. To qualify as a planet, an object must orbit the sun, be spherical in shape, and clear its orbit of other debris. Mercury, check. Venus, check. Earth, check. Pluto? Not quite. Pluto shares its orbital space with countless other icy bodies in the Kuiper Belt, a vast ring of objects beyond Neptune. In other words, Pluto is surrounded by cosmic neighbors, meaning it doesn't clear its orbit. Boom, Pluto gets demoted to dwarf planet status. It was a shocking moment. People felt betrayed. Some even mourned Pluto as if it had been erased from existence. But here's the thing. Pluto didn't go anywhere. It's still out there, spinning silently at the edge of our solar system, icy, mysterious, and incredibly fascinating. It just doesn't meet that very specific definition of a planet. Technically correct, but let's be honest, Pluto is still awesome. To picture this, imagine a messy neighborhood. The true planets are like kids who have cleared the entire yard to themselves. Plenty of space, no competition. Mercury, Venus, Earth, they dominate their territories. Pluto is like the kid in the crowded block, sharing space with dozens of other icy kids, quietly doing his own thing without clearing the street. The definition may have changed, but Pluto's cool factor hasn't. And let's not forget how fascinating Pluto actually is. Despite its tiny size and distant orbit, it has an atmosphere, mostly nitrogen, that expands and contracts as it moves closer and farther from the sun. Its surface is dotted with ice mountains and plains bigger than Texas. In 2015, NASA's Horizons mission flew past Pluto, giving us breathtaking images of its icy landscapes, deep valleys, and even a giant heart-shaped glacier named Tombaugh Regio, in honor of its discoverer. For a world so small, Pluto has personality, beauty, and mystery packed into its 2,377-kilometer wide surface. Pluto also has 5 known moons, the largest of which is Charon. Charon is so big compared to Pluto that some scientists call the system a binary planet, where Pluto and Charon orbit a point in space between them rather than one orbiting the other. That's right. Pluto is tiny, yes, but it's a heavyweight in the moon department, showing us that even small, distant worlds can have complex, dynamic systems. Now, imagine being a human trying to visit Pluto. Temperatures drop to around -230 degrees Celsius, colder than any place on Earth by far. The surface is frozen solid, and sunlight is a mere fraction of what we get on Earth. Yet, it's alive with icy activity, with mountains of water ice and nitrogen plains shifting in ways that suggest the world is more dynamic than we ever expected. It's a dwarf planet, yes, but Pluto is far from boring. There's something poetic about Pluto's status change. It went from planet to dwarf planet, from full member of the solar system lineup to the cosmic underdog. And yet, its charm has only grown. People still love Pluto. Memes, fan clubs, and pop culture references continue to celebrate this tiny world at the edge of the sun's reach. Pluto proves that status doesn't define importance. You can be small, distant, and technically demoted and still captivate the universe. So, next time someone proudly declares Pluto isn't a planet anymore, take a deep breath and smile. Yes, technically it's a dwarf planet. Yes, it doesn't clear its orbit like Mercury, Venus, or Earth. But Pluto is still out there, spinning silently, icy and mysterious, holding secrets we're just beginning to uncover. It has moons, an atmosphere, glaciers, mountains, and a personality all its own. Status may change, but Pluto's cool factor is eternal. In the end, Pluto reminds us that definitions and labels are useful, but they don't capture the full story. Tiny, distant, icy, and fascinating. That's Pluto. Dwarf planet or not, it's a world that has inspired generations, challenged our assumptions about what makes a planet, and continues to surprise us with its complexity. Small, yes. Demoted, yes. But utterly captivating, extraordinary, and endlessly worth exploring. So let's give Pluto a cheer, not for its planetary status, but for being Pluto, the cosmic underdog, the mysterious world at the edge of our solar system, the dwarf planet that continues to capture our imagination, hearts, and science curiosity. Pluto may not be officially a planet, but in the universe of cool, it's still a heavyweight champion.
All planets are round spheres. When most of us think of planets, our mental image is simple: a perfectly round ball spinning gracefully in space. Earth? Round. Mars? Round. Jupiter? Round. It's so ingrained that textbooks, models, movies, and even school songs make planets look like flawless spheres. You see them in diagrams, floating serenely in the solar system, and your brain assumes if it's a planet, it's a sphere. Easy, neat, satisfying. But then you meet the oddballs of the cosmos, and suddenly the universe laughs at your expectations. Enter Haumea, a dwarf planet lurking in the distant Kuiper belt. At first glance you might think, yeah, just another icy dot. But Haumea isn't a sphere. It's elongated, stretched like a cosmic rugby ball, or a potato hurtling through space. How did that happen? The secret lies in speed. Haumea spins incredibly fast, once every 4 hours, for a planet that's ridiculously fast. Gravity is trying to pull it into a sphere, but centrifugal force from its rotation is stretching it outward. The result? A world that's more of an oval than a ball, defying what we thought planets should look like. Picture it like this. Imagine you're spinning a lump of clay on a pottery wheel. Spin it slowly, and it forms a perfect sphere. Spin it faster, and it stretches, elongates, flattens. Haumea is like that, but on a cosmic scale. A world spinning so fast that its very shape rebels against gravity, refusing to be a tidy, round ball. And just like that, the universe reminds us that perfection isn't required. Planets don't have to be round. Some are quirky, weird, or downright odd-shaped. Haumea isn't just unusual for its shape. It also has a faint ring system and 2 moons. Its odd form complicates how scientists calculate its mass, rotation, and gravity. Unlike a typical spherical planet where mass is evenly distributed, Haumea's elongated shape spreads its mass unevenly, creating unique gravitational effects for its moons and ring particles. It's not just a funny-shaped rock, it's a complex system, a spinning, elongated world with its own miniature solar system. Haumea isn't alone in breaking the rules. Many smaller celestial bodies, dwarf planets, asteroids, and icy Kuiper belt objects are lumpy, elongated, or irregularly shaped. In fact, spherical perfection is actually rare when objects are small or spin fast. Earth-sized planets or larger tend to be round because gravity dominates their structure. But when objects are small, gravity isn't strong enough to smooth them out completely. Add rapid rotation, and you get weird shapes like Haumea. Now, let's bring this closer to home. Imagine spinning a basketball versus spinning a water balloon. The basketball resists deformation. It stays almost perfectly round. But spin a water balloon, and it bulges, stretches, and distorts. Haumea is like that water balloon, only millions of kilometers away, icy, and orbiting the sun in the distant reaches of the Kuiper Belt. It's a tiny reminder that the cosmos isn't neat, orderly, or predictable. Sometimes it's playful, messy, and a little weird. Here's another fun twist. Haumea's odd shape also affects how it looks from Earth. Its rapid rotation causes brightness variations as it spins. Astronomers can detect these changes in light, which is how they first realized it wasn't a sphere. Imagine a distant dot in the sky, flickering ever so slightly because it's spinning like a potato instead of rotating like a marble. That's science detecting the quirks of a world billions of kilometers away. A tiny potato-shaped beacon at the edge of our solar system. And Haumea's story teaches us an important lesson. The universe doesn't follow our expectations. We like simple rules. Planets are round, orbits are neat, stars twinkle, comets tail away from the sun. But reality is messier, stranger, and infinitely more fascinating. Planets can be rugby balls, asteroids could be potatoes, and moons can orbit in ways that defy casual logic. These cosmic oddballs challenge our assumptions, forcing scientists and anyone looking up at the night sky to rethink what we thought we knew. So, the next time someone confidently declares, "All planets are round spheres," you can smile, nod, and think of Haumea spinning far out in the Kuiper Belt. Tiny, icy, elongated, and absolutely defying expectations. It's a world that laughs at simplicity, proving that cosmic variety is the norm, not the exception. And that's the beauty of space. Even tiny, distant objects can be astonishing, unusual, and mind-bending. In the end, Haumea reminds us that size, spin, and distance can bend the rules of planetary shape. Gravity does a lot of work in the universe, but it's not absolute. Rotation, composition, and mass distribution all influence how a planet or dwarf planet looks. Some planets are perfect spheres, others are rugby ball-shaped anomalies with rings and moons, spinning silently in the darkness. Haumea is a cosmic reminder. The universe loves variety, quirks, and surprises. Perfect spheres? Optional. Weird, elongated cosmic oddballs? Absolutely.
The moon has no atmosphere. When most of us think about the moon, we imagine a cold, barren, airless rock floating in space. No clouds, no wind, no breathable air. Classic moon imagery. Astronauts hop around in bulky suits, the surface is dusty, and for all practical purposes, it seems completely lifeless. For decades, that image stuck. The moon has no atmosphere. It's such a simple line, repeated in textbooks, movies, and science classes, that almost everyone takes it as fact. But like many things in space, the truth is a little stranger than we imagine. Here's the twist. The moon does have an atmosphere. Sort of. Technically, it's called an exosphere, and it's one of the thinnest, most tenuous layers of gas you can imagine. But calling it an atmosphere might be a little misleading.
The difference is huge. Earth's atmosphere is dense, filled with trillions of air molecules bouncing around, creating wind, weather, clouds, and breathable oxygen. The Moon's exosphere, on the other hand, is almost nothing. Individual atoms of gases like helium, neon, hydrogen, and argon drift across the surface, but they're so sparse that they rarely collide with each other. It's technically present, but if you stood on the Moon, you wouldn't feel it. You wouldn't see it. You wouldn't even notice it. In fact, if someone told you, hey, the Moon has an atmosphere, you'd probably look at them like they just suggested the Moon has a Starbucks. So why did we all grow up believing the Moon is completely airless? Well, it comes down to experience. The Moon has no weather like Earth. No storms, no rain, no breezes. Astronauts don't float around coughing in clouds of dust, and there's no wind to ruffle the lunar regolith. For all observable purposes, it's airless, so scientists and educators simplified the truth for easier teaching. No atmosphere. And honestly, that simplification makes sense for practical purposes. But in reality, the Moon's exosphere exists. It's just invisible, ghostly, and extremely tenuous. Imagine this. You're standing on a football field, and someone sprinkles a few grains of sugar across it. Those grains are the Moon's exosphere, scattered so thinly across a massive area that you'd never notice them without special instruments. Or picture a single sheet of paper floating in the middle of a stadium. Technically, it's there, but practically, invisible. That's what the Moon's exosphere is like. It's a cosmic whisper, almost non-existent, but still technically present. The exosphere isn't permanent or static. The Moon's environment is constantly bombarded by the solar wind, streams of charged particles from the sun that knock atoms off its surface and temporarily replenish its exosphere. Even small meteoroid impacts can create transient clouds of gas as atoms are ejected into the exosphere. So, in a way, the Moon's atmosphere is alive in the most subtle, ephemeral sense, a whisper of activity rather than a gust of wind. This ultra-thin exosphere has some surprising consequences. For instance, instruments left behind by Apollo astronauts like retroreflectors used to bounce lasers off the Moon have survived for decades. On Earth, atmospheric particles, wind, rain, and weather wear down surfaces over time. On the Moon, there's almost nothing to cause corrosion or erosion. That's partly thanks to its tenuous exosphere. It's technically an atmosphere, but it's more like a cosmic protective vacuum, keeping some human artifacts intact for generations. Now let's put this in perspective with humor and imagination. So technically, the Moon has an atmosphere. Can you breathe it? Absolutely not. Can you feel it on your skin? Nope. Would it ruffle your hair? Only if you brought a leaf blower from Earth. In fact, the Moon's atmosphere is so thin it might as well be called a cosmic whisper. Barely there, barely detectable, and yet technically present. It's the universe's way of saying, hey, even the airless worlds get a tiny nod. Despite its faintness, the Moon's exosphere is a perfect example of how space defies simple explanations. You grow up hearing no atmosphere, but the truth is subtle and fascinating. It teaches us that space is rarely black and white. Even worlds that seem completely dead have quirks, invisible features, and tiny traces of activity. The Moon, our familiar satellite, is a quiet reminder that even airless worlds aren't truly empty. They're just whispering, almost imperceptibly, in a language we're just beginning to understand. So the next time someone confidently says the Moon has no atmosphere, you can smile and say, technically, it does. It's just so thin you'd never notice without sensitive instruments. It's like pointing out a single blade of grass in the middle of a desert. The moon may feel lifeless, but its exosphere is there, a ghostly, wispy reminder that even the most barren worlds have a hint of presence. In the end, the moon's exosphere might be invisible and inconsequential to humans standing on its surface, but it's an important part of its story. It's a subtle layer that interacts with solar winds, meteoroid impacts, and human instruments. It reminds us that labels like no atmosphere are convenient simplifications, but the truth is more fascinating, more nuanced, and a little just stranger than we imagined. The moon isn't truly airless, it's just whispering. And that's the beauty of space. Even worlds we think we know perfectly, like our moon, have secrets. Tiny atoms floating silently, barely interacting, forming a faint exosphere that's technically an atmosphere, but practically nothing at all. The moon teaches us that even airless worlds can have life of a kind we don't see, don't feel, and can barely detect. It's a quiet cosmic hum, almost imperceptible, but endlessly fascinating.
Mars is red because of iron alone. Look up at the night sky, and one star, or rather one planet, jumps right out at you. That fiery glowing dot is Mars, the famous red planet. From school books to science fiction movies, Mars is instantly recognizable for its striking red color. It's what makes it special, what makes it memorable, and what earns it a spot in every space-loving person's imagination. And if you've ever wondered why Mars is red, the simple answer people usually give is iron. Iron rusts, Mars has iron, Mars is red. Easy. Done. Right? Well, not exactly. There's a lot more going on than just plain old iron sitting on the surface, and understanding that makes Mars even cooler. Yes, iron is the key ingredient, but it's not as simple as a rusty nail lying around. Mars's red color comes from iron oxides, a complex result of chemistry, environmental conditions, and billions of years of planetary history. Basically, tiny iron minerals in the soil and rocks have reacted over time with oxygen, cosmic radiation, and perhaps traces of water, forming compounds like hematite and magnetite, which give Mars its rusty, reddish-orange appearance. This isn't just casual rusting like on your bike in the rain. It's a planetary-scale oxidation process that has taken billions of years to paint the entire planet in shades of red, orange, and brown. To picture it, imagine sprinkling a fine layer of rust powder across the entire planet. Dust storms pick up these tiny iron oxide particles and scatter them across Mars's surface. So the red color isn't confined to a few regions. It's literally everywhere, from the poles to the equator. Up close, the ground might look dusty, granular, and brownish. But from space, all that iron oxide dust combines into a strikingly red appearance that gives Mars its iconic nickname. Mars isn't just red for aesthetic reasons. It's red because of chemical processes at an astronomical scale. The story of Mars's red hue is also tied to its environment. Mars is dry, cold, and winds constantly move the fine dust across the planet. This means that giant dust storms can form, sometimes covering the entire planet for months at a time. When that happens, Mars's red color dominates the solar system view. Imagine looking through a red-tinted fog that spans the entire planet. That's what Mars experiences during some of these massive storms. Those iron oxide particles are not just cosmetic. They actively interact with sunlight, the atmosphere, and the weather, shaping what we see from Earth.
Interestingly, Mars's color isn't completely uniform. Some regions appear darker, almost brown, while others are lighter, almost orange. These differences are due to the specific types of iron oxide minerals in each region and how some light reflects off the dust. Hematite-rich areas, for example, can appear darker and metallic, while other areas with finer dust look more like soft, rusty sand. That means every time we look at Mars, we're seeing a planet painted by billions of years of chemistry and environmental change, a dynamic canvas, not just a static red ball. Now let's think about this casually. Next time someone says, "Mars is red because of iron," you can nod politely and then add, "Yeah, but it's a very specific, highly processed, billions of years in the making rust, not your kitchen nail rusting in the rain." There's a kind of poetic beauty in that. Mars's red isn't a simple accident. It's a record of its history, a story written in minerals, dust, and chemical reactions stretching across eons. Every grain of iron oxide tells the tale of oxidation, planetary evolution, and cosmic weathering. It's not just a color, it's a planetary autobiography. Another fascinating aspect is that Mars's red dust isn't static. It moves, shifts, and interacts with the planet's thin atmosphere. That's why the planet can look brighter or duller depending on the season or the occurrence of dust storms. The red color is alive in a sense. It's dynamic, constantly shaped by wind, weather, and chemical changes. The surface isn't just painted red. It's actively maintaining that color through natural processes. Mars's iconic color also has implications for science and exploration. Scientists studying Mars must understand the composition of the iron oxides to learn about its geological history, past water presence, and even clues about potential habitability. For example, regions rich in hematite often indicate past interactions with liquid water, offering tantalizing hints about the red planet's ancient environment. The rusty dust isn't just beautiful, it's scientifically meaningful, getting us a direct link to understanding Mars's story. So when you look at images of Mars glowing brilliantly in its red-orange glory, remember, it's more than just iron sitting around. It's oxidation chemistry at a planetary scale, shaped by solar radiation, dust movement, and perhaps ancient water. Mars's red color is a visual shorthand for billions of years of geological and chemical history. That iconic color isn't accidental. It's a record, a signature, and a kind of cosmic fingerprint. In the end, Mars reminds us that space isn't simple. We love easy answers. Mars is red. Jupiter has stripes. The moon has no air. But the truth is often more fascinating, more nuanced, and far stranger than the simple labels we grew up with. Mars's red color tells a story, and understanding it means appreciating chemistry, planetary processes, and the dynamic nature of the cosmos. That rusty glow isn't just for looks. It's Mars showing off its history. So the next time someone casually says, "Mars is red because of iron," smile and nod, but remember to think bigger. It's not just rust, it's billions of years of planetary evolution, chemical processes, and cosmic weathering all rolled up into one iconic red glow. Mars isn't just the red planet for nothing. Its color is a scientific masterpiece, a combination of iron chemistry, dust storms, and ancient history that makes it one of the most visually and scientifically captivating worlds in our solar system.
Spacewalks are easy. When most of us watch footage of astronauts outside the International Space Station, it looks effortless. They float gracefully against the backdrop of Earth, tethered to the station, hands moving as if they're performing a zero-gravity ballet. They twist, turn, and drift around like it's all fun and games. Movies and documentaries make it look serene, almost meditative. You might even think, wow, being an astronaut on a spacewalk must be amazing and easy. But if you believe that, you are about to have your mind blown. Spacewalks are far from easy. They're one of the most physically and mentally demanding activities humans have ever done. First off, let's talk gear. Astronauts don't just float around in pajamas. They wear extravehicular mobility units, EMUs, basically self-contained spacesuits that keep them alive in the vacuum of space. On Earth, these suits weigh over 280 pounds. In microgravity, you don't feel that weight in the same way, but you do feel the bulk. The suit is stiff, pressurized, and layered with insulation, life support, and protection against micrometeoroids and radiation. Moving your arms, bending your legs, and gripping tools in that suit is like trying to do yoga while wearing a medieval knight's armor. Simple tasks, like turning a bolt or carrying equipment, take more effort than you'd imagine, because every movement fights the suit's stiffness. Now imagine doing that while floating hundreds of kilometers above Earth. There's no floor to push off of, no friction to help stabilize you. Every motion has to be carefully calculated, or you risk spinning out of control. Astronauts often joke that working in space is like swimming in molasses while wearing a weighted diving suit. And yes, swimming in molasses sounds like an extreme workout. Your muscles tire fast. Fatigue sets in, and your body has to work overtime just to perform what would be routine tasks on Earth. And remember, these spacewalks last 6 to 8 hours, sometimes even longer. That's a long time to be moving continuously, carefully, and deliberately in a suit that doesn't bend naturally with your body. Then there's the life support system. Your suit isn't just for protection. It's your entire survival kit. It controls oxygen, removes carbon dioxide, regulates temperature, and even handles humidity. You can't simply step out of it to take a break or wipe sweat from your face. Astronauts have to pace themselves, hydrate before the walk, and mentally prepare for the marathon ahead. One wrong move, and you could damage the suit, compromise the life support, or end up drifting away from the station. That's why astronauts spend hundreds of hours training underwater in neutral buoyancy pools to simulate microgravity and practice every motion before they attempt it for real. And if that wasn't enough, there's radiation. Space is full of high-energy particles from the sun and beyond, which can be deadly if you're not protected. The Earth's magnetosphere shields us on the surface, but astronauts on a spacewalk are outside most of that protection. Solar flares can release intense radiation in minutes, and the EMU can only do so much. Timing, planning, and constant monitoring are critical to stay safe. A sudden spike in radiation could force an immediate retreat, cutting the spacewalk short and potentially putting the astronaut in danger. Even navigation and stability are tricky. On Earth, you have gravity, friction, and feedback from your muscles to help you maintain balance. In space, those cues are gone. Astronauts have to rely on tethers, handrails, and careful planning to move along the station. The tiniest miscalculation can send them spinning. And with Earth spinning silently below,
Every glance is both breathtaking and distracting. No wonder astronauts describe the first moments outside of the station as surreal. Now let's bring it down to something relatable. Imagine doing a 6-hour workout in a stiff, pressurized, self-contained suit, with the risk that one small slip could send you floating into a vacuum with no hope of rescue. Sweat builds up inside, your muscles ache, your hands get tired, and there's no bathroom break. That's basically what a spacewalk is like. And yet, astronauts perform these extreme activities routinely, often with incredible precision, installing equipment, repairing satellites, or conducting experiments. What looks graceful on video is actually a mix of endurance, strength, concentration, and nerve. Here's a fun mental image. When you see an astronaut gliding in orbit, think of them as a ballet dancer. Yes, but a ballet dancer carrying a 280-pound suit, life support backpack, and a toolbox while performing pirouettes on a tightrope suspended above a giant glowing marble called Earth. That's extreme and dangerous. Every move counts. There's no second chance. Despite the risks, spacewalks are essential. Without them, repairs to the ISS, maintenance of satellites, and construction of new modules wouldn't be possible. They're the ultimate combination of human skill, technology, and courage. But the takeaway? Spacewalks are far from easy. They're exhausting, risky, and require meticulous preparation, extreme physical conditioning, and nerves of steel. The video footage might make it look peaceful, but in reality, every second is a careful dance with physics, life support, and the vacuum of space. So next time you see an astronaut floating outside the ISS, watching Earth spin silently beneath them, take a moment to appreciate what's really happening. Behind that serene exterior is hours of intense physical effort, constant vigilance, and the ever-present awareness of danger. It's awe-inspiring, breathtaking, and utterly human, but it's definitely not easy. Spacewalks may look effortless on film, but they are one of humanity's most extreme and dangerous endeavors. Bulky suits, fatigue, radiation, and the ever-present risk of drifting away into the void make them a monumental challenge. And yet, they continue to be performed with remarkable skill, reminding us how much humans can achieve when technology and courage meet in the harshest environments imaginable. Spacewalks, not as easy as they look, but absolutely incredible to watch.
Astronauts age slower in space. Sci-fi fans, listen up. One of the most popular space myths is that astronauts age slower in space. You've seen it in movies. Astronauts go on long missions, come back from the stars, and suddenly they're younger than their friends who stayed on Earth. Time travel, anti-aging, suspended youth. It's like the universe's ultimate fountain of youth. Tempting, right? But before you book your one-way ticket to orbit in search of eternal youth, let's set the record straight. Here's the science behind the idea. Einstein's theory of relativity says that time isn't fixed. It can stretch or compress depending on speed and gravity. That means the faster you move, the slower time passes for you relative to someone who's not moving as fast. And similarly, the weaker the gravitational field you're in, the slower time moves for you compared to someone in a stronger field. This phenomenon is called time dilation, and yes, it's a real thing. The universe really does play tricks on time. So technically, if you blast off into space and orbit Earth in a spaceship, your clock ticks a tiny bit differently than your friends' clocks back home. That's where the idea comes from that astronauts age slower in space. Sounds like a sci-fi dream come true, right? Well, there's a catch, or more accurately, a giant caveat. The effect is minuscule at the speeds humans currently travel. Astronauts aboard the International Space Station orbit Earth at roughly 28,000 kilometers per hour. That's super fast by human standards, but in terms of relativity, it's a tiny fraction of the speed of light, which is about 300,000 kilometers per second. At these speeds, the difference in time experienced by astronauts versus people on Earth is fractions of a second over the course of an entire year. To put it another way, if you had a twin on Earth while you spent a year in the ISS, the age difference would be a few milliseconds. Blink, and you'd miss it. A few milliseconds over an entire year is the closest thing to cosmic anti-aging that real-life astronauts get. Even gravity plays a role. Space might seem weightless, but gravity is still very much at work. The ISS is in low Earth orbit, about 400 kilometers above the surface. That's above the atmosphere, but still well within the reach of Earth's gravity. Time dilation due to weaker gravity at that height is tiny as well, barely noticeable. The combined effect of speed and microgravity does technically make astronauts age slower, but the difference is so small it's completely imperceptible without precise atomic clocks. Now, imagine what it would take to actually see a noticeable difference in aging. To get significant time dilation, you'd need to travel at near light speed, close to 300,000 kilometers per second. At that point, relativity starts stretching time in a dramatic way. You could spend months on a spaceship zipping near light speed, and when you return to Earth, decades might have passed for everyone else. That's the kind of anti-aging effect that sci-fi loves to portray. But we're nowhere near achieving that kind of speed with current technology. Our rockets are fast for humans, but in the cosmic scale of relativity, they're crawling. Let's put this in perspective with something relatable. Imagine two identical twins. One stays on Earth, the other spends a year orbiting the planet in the ISS. After 12 months, they reunite. The twin who went to space hasn't magically lost years. The difference is about a few milliseconds. You could sneeze, blink, or check your phone, and you'd pass that tiny time gap without noticing. It's real, but it's basically invisible. So why do people think astronauts age slower in space in the dramatic movie-style way? Well, it's all about storytelling and exaggeration. Sci-fi takes the kernel of truth, relativity exists, and blows it up into a narrative where astronauts return decades younger than their peers. It's fun, imaginative, and a cool way to explore time travel themes. In reality, the anti-aging effect at current spaceflight speeds is more like cosmic micromanagement of milliseconds than a true fountain of youth. Here's a fun thought. Space isn't giving you youthful skin or the ability to dodge wrinkles. The real perks are things like stunning views of Earth, the experience of micropravity, and bragging rights about floating in orbit. Maybe that counts as a different kind of anti-aging. Your soul feels younger after seeing Earth from above, even if your watch says you're the same age. In conclusion, astronauts technically age slightly slower in space thanks to the principles of Einstein's relativity. But the difference is so tiny at the speeds humans currently achieve that it's practically meaningless in daily life. True, noticeable anti-aging would only occur at speeds we can't reach yet, near the speed of light or in extreme gravitational fields far beyond our current capabilities. For now, space remains awe-inspiring, beautiful, and full of mind-bending physics, but it won't make you young again. So the next time you hear someone claim, astronauts age slower in space, you can smile and nod because they're technically correct, but add, it's by a few milliseconds over a year. Don't quit your skincare routine just yet. Space is magical. It's strange and it bends time in ways we can barely imagine. But in terms of human aging, it's a cosmic tease more than a miracle cure.
Time may bend, clocks may tick differently, and relativity may play tricks, but astronauts still grow old just like the rest of us. The difference is just microscopic. And maybe, in that tiny fraction of a second, space gives a wink to the humans daring enough to explore it.
You can hear someone scream in space. You know the scene. An astronaut drifts too far from their spacecraft, a villain appears, or a cosmic disaster strikes. Then comes the scream, echoing across the void. Ah! Dramatic, terrifying, and completely impossible. Sorry, Hollywood, but space is not a giant surround sound theater. Not even close. Here's the science behind why. Sound, as we know it, is a wave. Waves need something to travel through, a medium like air, water, or a solid object. On Earth, sound waves push against air molecules, bouncing from one to the next until they reach your ear. That's why your voice travels when you yell, or why music reaches your ears from a speaker. But space is a vacuum. There's no air, no water, no molecules of any kind to carry the vibrations of sound. Zip, nada, silence. So, if someone outside your spacecraft screams as loud as they possibly can, you won't hear a thing. Not a whisper, not a wail, not even a tiny squeak. The sound simply cannot travel. You'd see the person flail their arms, mouth open in terror, but it would be eerily silent. It's the kind of silence that's both beautiful and terrifying, a reminder of just how empty space really is. Now, you might be wondering, wait, but astronauts talk in spacewalk footage. How do we hear them? Good question. That's because astronauts don't rely on sound traveling through the vacuum. Instead, their voices are transmitted electronically through radios in their helmets. The microphone picks up vibrations from the astronaut's voice, converts them into radio signals, and sends them to the other astronaut or mission control. So when you hear an astronaut shout, it's not the screen traveling through space, it's the radio transmitting their voice electronically. Science magic. Here's a cool mental image. Picture two astronauts drifting in orbit, floating silently above the glowing Earth. One yells, waving wildly, but all the other hears is nothing. Complete, absolute silence. Then the radio crackles, "Houston, we have a problem." That's the only sound breaking the eerie void. The contrast between motion and absolute silence is actually one of the most haunting aspects of real spacewalks. You can take it one step further. Technically, sound can travel through solid materials even in space. So if two astronauts were holding the same metal beam, vibrations from one's voice could transmit through the metal and be heard by the other. But that's very limited and only works through physical contact, not across the empty space between them. So screaming into the void, still silent. This silence isn't just a fun science fact. It changes how space feels. Imagine being outside your spacecraft, tethered by a thin cord, staring down at Earth spinning silently beneath you. There's no wind, no background noise, no hum of engines, just the endless void of silence stretching in every direction. It's beautiful, humbling, and slightly terrifying. And that's what makes spacewalks look so cinematic in a different way, because in reality, it's not the loud, action-packed vacuum you see in movies. It's serene, still, and completely quiet. Hollywood loves to cheat. Explosions roar, alien ships hum, astronauts scream, and lasers zip through the vacuum with sound. It's thrilling, yes, but it's a physics violation on a planetary or cosmic scale.
In reality, no matter how dramatic the event, space itself remains silent. That's part of the majesty and the danger. You can't rely on your ears to detect anything. Instead, astronauts have to depend on instruments, radios, and their own senses to know what's happening. Let's be honest. Silence in space is a little eerie. Think about the vacuum outside your helmet. No molecules to vibrate, no air to carry noise, just infinite emptiness. If you're a fan of cosmic horror, this is the ultimate setup. A human scream in a vacuum is a gesture without sound, pure visual terror. Imagine watching someone drift away, panic evident, but the universe doesn't even flinch. That's a different kind of terrifying than any movie can create. So, next time you watch a space movie or a sci-fi show, remember, the screams, explosions, and booming engines are pure fantasy. In real space, you'd hear absolutely nothing without electronic help. It's not a lack of imagination, it's just physics. Space is silent, completely silent. The vacuum is unforgiving that way, and any sound you think you hear in orbit is either inside the spacecraft or communicated through radio waves. In summary, you can forget the terrifying screams, the echoing booms, and the Hollywood soundtracks. Space doesn't carry sound. It's a silent, vast, and hauntingly beautiful void. If anything, the silence is more dramatic than the action scenes, more awe-inspiring than any explosion, and certainly more humbling. That absolute quiet reminds us how alien and extreme space really is, and why astronauts rely on technology and instruments to hear anything at all. So when someone tells you that you can hear someone scream in space, just smile and shake your head. No, you can't. There's no medium for sound waves. Only the haunting, infinite, and silent cosmos awaits. And honestly, that's way cooler than any movie sound effect.
Astronauts drink bottled water in space. When most of us picture astronauts in space, we imagine them casually sipping water from shiny bottles or pouches, floating gracefully in microgravity while enjoying the ultimate refreshment. Movies, TV shows, and cartoons all love that image. An astronaut pops open a straw, takes a sip, and smiles at the Earth spinning silently beneath them. Sounds neat, right? Comfortable, familiar, totally normal. But here's the shocking reality. Astronauts don't drink bottled water in space, at least not in the way we think. In fact, the water astronauts drink on the International Space Station is mostly recycled from sweat, urine, and even the humidity in the air. Yeah, that's right. Space hydration is one of the weirdest yet most ingenious things humans have ever figured out. Before you freak out, let's unpack it. First, let's understand the problem. Water is heavy. On Earth, we take it for granted because we can just turn on a tap. But in space, every kilogram matters. Every extra liter of water you carry into orbit increases launch costs and complexity. You can't exactly have a faucet flowing endlessly on the ISS, so astronauts rely on a closed-loop system designed to recycle almost every drop of water available. Think of it as a high-tech, extreme version of a water filter that makes every molecule count. Here's how it works. The ISS has a water recovery system, WRS, that captures moisture from multiple sources: exhaled breath, sweat, condensation, and even urine. The system then purifies the water through several stages, removing impurities, bacteria, and anything else you wouldn't want in your cup. After a complex journey through filters, chemical treatments, and ultraviolet light, the water that comes out is completely safe to drink. NASA proudly calls it potable water, which is just a fancy way of saying totally fine for astronauts to sip without fear. Now, let's talk about urine. It sounds gross, but here's the fun part. Astronauts' urine is scientifically recycled into drinking water, and while your brain might be screaming, "Ooh," the system works so well that the water is indistinguishable from any purified drinking water on Earth. In fact, about 90% of the water astronauts drink comes from recycled sources. Sweat, exhaled breath, that moisture contributes too. Essentially, astronauts drink water that has been reclaimed from the environment of the space station itself, keeping the station hydrated without needing constant shipments of fresh water from Earth. Imagine it like a futuristic magic trick. Every time an astronaut breathes, tiny droplets of water leave their lungs. That water vapor gets collected by the system, filtered, and returned as drinkable water. Every drop counts. Every bit of sweat that clings to a spacesuit or body gets recycled too. It's not glamorous, but it's incredibly efficient and honestly, kind of genius. Without this closed-loop system, long-term life in orbit would be nearly impossible. And here's a little mental image for fun. Picture floating in microgravity, holding a water pouch. You squeeze it, sip, and think about how that water might have once been in someone else's sweat or urine. Weird? Sure. Ingenious? Absolutely. That's the reality of living in space. Humans are resourceful, and space makes you rethink everything you thought was basic, including drinking water. There's also a psychological component to this. Astronauts are trained extensively on how the system works, so they don't feel grossed out. The moment the water comes out of the filtration system, it's chemically and biologically pure. They drink it just like you drink bottled water on Earth. And while it might sound icky from our perspective, astronauts are focused on survival, efficiency, and sustainability. In space, practicality always wins over squeamishness. Interestingly, movies and cartoons often ignore this part. Hollywood loves showing astronauts sipping from bottles or using straws without ever mentioning the recycling system. It's visually simpler, more relatable, and lets audiences focus on adventure. But in reality, every drop of water aboard the ISS is part of a carefully managed system designed to make human life sustainable in orbit. Without it, long-duration missions like those planned for the Moon or Mars wouldn't be feasible. So, next time someone brags about their bottled water on a hot day, remind them that astronauts drink recycled pee and sweat and somehow survive just fine. It might sound gross, but it's one of the most brilliant examples of human engineering in space. Closed-loop hydration, microgravity management, and advanced filtration systems allow astronauts to live in orbit for months at a time without running out of the most essential resource, water. To sum it up, bottled water in space is mostly a myth. Astronauts rely on an incredible high-tech recycling system that turns urine, sweat, and even the air's humidity into safe, drinkable water. It's efficient, essential, and a little bit mind-blowing. Space forces humans to rethink even the most basic things, like staying hydrated. And in doing so, we discover just how clever our technology has become. Gross? Maybe. Fascinating? Definitely. Ingenious? Absolutely. Living in space is full of surprises, and drinking recycled water is one of them. The next time you see an astronaut casually sipping from a pouch, remember that liquid is the product of science, engineering, and the reality of living in a place where resources are limited and every drop counts. Space doesn't allow for convenience like we have on Earth. Instead, it challenges us to innovate, adapt, and marvel at the systems we've created to survive among the stars. In the end, it's not just about staying hydrated. It's a testament to human ingenuity. Astronauts drinking water reclaimed from sweat and urine is one of those facts that sounds like science fiction, but is actually science fact. It's a little gross, a lot smart, and a perfect example of how life in space isn't what we think it is, but it's working flawlessly every single day.
Space is completely safe. When most people think of space, they imagine serenity, astronauts gracefully floating above Earth,
stars twinkling in the distance, and an endless calm expanse stretching as far as the eye can see. It looks peaceful, like a cosmic vacation spot where the toughest decision is which side of the spacecraft to float on. But here's the reality check. Space is anything but safe. That beautiful vacuum hiding beyond our atmosphere is a constant battlefield of invisible threats. First, let's talk about radiation. On Earth, we're lucky. Our planet has a thick atmosphere and a protective magnetic field that shields us from the sun's most dangerous particles and cosmic rays from deep space. In orbit or anywhere outside the protective layers, it's a whole different story. Astronauts are bombarded by solar radiation and cosmic rays, high-energy particles that can penetrate spacecraft walls and even human tissue. Over time, this exposure increases the risk of cancer, damages DNA, and can harm critical systems in the body. And it's not just hypothetical. This is a very real concern that NASA carefully monitors. Astronauts' missions are planned with radiation exposure limits, and long-term missions, like those to Mars, require incredibly detailed safety measures to minimize the risk. Now, radiation might sound like an abstract threat, but it's relentless. Unlike weather or predators on Earth, it's invisible and constant. Imagine floating in orbit, staring down at Earth's beauty, while particles faster than a speeding bullet are zipping through your spacecraft. There's no warning, no noise, just invisible energy that can punch through your body if you're unshielded. That's not exactly the relaxing space experience we tend to imagine from photos. And if radiation isn't enough to make you rethink space as a safe place, consider micrometeorites. These aren't the giant meteors that explode in movies. They're tiny, often microscopic pieces of rock or metal. But here's the catch. They travel at insane speeds, sometimes tens of thousands of kilometers per hour. At that velocity, even a particle smaller than a grain of sand can carry enough energy to punch through metal, glass, or spacesuits. Essentially, space is littered with countless high-speed bullets that you can't hear, see, or dodge. The serene floating you see in movies, it's a visually stunning scene hiding a constant threat of tiny, deadly collisions. Space agencies have developed clever solutions to counter these dangers. Spacecraft and the International Space Station use multi-layered shielding to absorb or deflect high-speed micrometeorites. Special materials and engineering designs help protect astronauts from radiation, though shielding can only reduce exposure, not eliminate it. That's why mission durations are carefully planned. Astronauts aren't just floating in bliss. They're in a carefully monitored environment, constantly guarded against invisible dangers. Even inside the spacecraft, threats persist. Radiation still penetrates, and micrometeorites can sometimes strike small external components. Engineers have to balance weight, materials, and safety features because adding too much shielding makes the spacecraft heavier and harder to launch. Every layer of protection is a trade-off, a calculation of risk versus practicality. In other words, space travel is a delicate dance with danger, even when astronauts appear perfectly safe floating in orbit. Here's a mental image. Picture an astronaut stepping outside for a spacewalk. Around them, the stars are dazzling, Earth is breathtaking, and everything looks calm. But around that serenity, invisible bullets, tiny fragments of cosmic rock, and deadly radiation are constantly threatening them. One wrong move, a failure in shielding, or a high radiation flare from the sun could be catastrophic. It's not fear-mongering. It's physics, and it's very real.
Movies love to ignore these details. Explosions are loud, lasers hum, spaceships appear indestructible. Hollywood presents space as a playground for adventure, where danger is mostly dramatic and visible. Reality? Space is a harsh, silent, invisible gauntlet. Every second outside a spacecraft, every orbit around Earth is a test of engineering, technology, and human resilience. The silent vacuum doesn't forgive mistakes, and there's no second chance if shielding fails. Even something as small as space dust can be deadly. Astronauts can't just dodge it or hear it coming. Every particle has kinetic energy, and at orbital speeds, even a tiny speck is like a high-powered bullet. Combine that with radiation exposure, and you begin to understand why space travel requires extreme caution, meticulous planning, and constant monitoring. It's beautiful, yes, but it's also relentlessly dangerous. So the next time you see a photo of astronauts floating gracefully against a backdrop of Earth and stars, remember, the calm you're seeing is just the surface. Beyond that visual serenity lies radiation, micrometeorites, and the complete absence of the protective layers we take for granted on Earth. Every moment in space is a managed risk. Every mission is a triumph of engineering, safety measures, and human resilience against an environment that is fundamentally hostile. In short, space is far from safe. Stunning views don't make radiation harmless, and silence doesn't make high-speed micrometeorites less deadly. The universe outside our atmosphere is a constant reminder of how extreme and unforgiving it is. Astronauts appear peaceful in orbit, but they rely on sophisticated engineering, careful planning, and continuous monitoring to survive. Space isn't a playground. It's a hostile frontier, stunningly beautiful, but constantly threatening life in ways we can't even imagine. So when you think about space being calm and safe, think again. It's a silent, invisible battleground. Every dazzling sunrise over Earth, every sparkling star comes with a hidden price. Radiation, micrometeorites, and the void itself are relentless. Space travel is an achievement not just of exploration, but of managing danger where no human instinct can protect you. Beauty comes with risk, serenity comes with vigilance, and survival requires both brains and engineering. In the end, space is never completely safe. Its majesty and tranquility are just the visible face of an invisible battleground, reminding us why human spaceflight is such an incredible achievement. Astronauts aren't just adventurers, they are warriors of the void, floating gracefully while constantly navigating dangers the rest of us can barely imagine.
Black holes are giant vacuum cleaners. If you've ever watched a space movie, scrolled through a science article, or even just daydreamed about the universe, you've probably imagined black holes as giant, universe-devouring vacuum cleaners. You know the scene. A star drifts too close, a spaceship zooms by, and suddenly, whoosh! Everything gets sucked into the black hole, never to be seen again. Sounds terrifying, right? Like some unstoppable cosmic monster. Well, not quite. Let's break it down. First, it's easy to see why this myth exists. Black holes have an almost mystical reputation. Their name alone sounds scary. Black hole. Combine that with sci-fi media showing them swallowing stars and planets, and even entire ships. And it's no wonder people think there's some sort of universal vacuum. Movies love that imagery because it's simple, dramatic, and frightening. But the reality is far more fascinating and way less indiscriminately destructive. A black hole is, at its core, an object of immense density and gravity. It's formed when a massive star collapses under its own gravity, compressing matter into an incredibly small volume. The result is an object so dense that the gravitational pull near it becomes extreme. Here's the kicker. Black holes don't randomly suck in everything nearby. Their gravity works the same way as any other massive object, like a star or planet. The difference is that their gravitational influence is concentrated in a tiny space, so the pull gets extreme as you get very close. This is where the concept of the event horizon comes into play. Think of it like an invisible fence surrounding the black hole. Step outside the fence and you can orbit, float, or even fly by safely. Cross the fence, the event horizon, and there's no turning back. That's where things start getting dramatic. Objects inside this boundary are trapped forever, including light, which is why black holes appear black to us. But outside the event horizon, you're perfectly safe. Stars, planets, and even entire solar systems can orbit nearby without ever being swallowed. Let's make a mental image. Imagine a black hole as a cosmic extreme sports park. The event horizon is a strict "don't cross this line" sign. Outside, you can orbit safely, enjoying the thrill and the view. Step inside, and you're in a point of no return, a place where gravity wins and escape becomes impossible. So, those movie scenes of black holes sucking up entire star clusters, total exaggeration. The universe isn't that careless. Here's a fun twist. Astronomers have actually observed stars safely orbiting black holes. One famous example is the stars orbiting Sagittarius A*, the supermassive black hole at the center of the Milky Way. These stars move incredibly fast and experience strong gravitational effects, but they don't get sucked in because they stay outside the event horizon. They even help scientists calculate the mass and properties of black holes, proving that gravity diminishes with distance just like with any other massive object. And for the record, black holes come in various sizes. Some are just a few times more massive than the Sun, while others, supermassive black holes, are billions of times the Sun's mass. No matter the size, the principle is the same. The gravitational pull only becomes dangerously strong very close to the event horizon. Far away, their gravity behaves just like that of a regular star, meaning your spaceship or planet has nothing to worry about unless it drifts too close. You might be thinking, so black holes aren't universal vacuum cleaners. Got it, but are they still dangerous? Absolutely, but only if you venture near. Tidal forces near the event horizon can stretch objects in a process called spaghettification. Yes, literally stretching them into long, thin shapes. It's extreme, fascinating, and something that happens only near the point of no return. Outside of that, the universe is safe. You can orbit, observe, and even marvel at the black hole without ever being consumed. Here's a little humor for perspective. No, your lost socks aren't drifting near a black hole waiting to vanish. Your house, car, and Earth itself are safe. Black holes aren't indiscriminate cosmic vacuum cleaners. They're like nature's extreme sport with very strict rules. Respect the event horizon, stay at a safe distance, and you can orbit forever without being eaten. Movies often exaggerate black holes for drama, and that's fine. It makes for thrilling visuals. But the real physics is far cooler and more nuanced. A black hole isn't a monster indiscriminately devouring everything. It's an object of extreme density, intense gravity, and fascinating physics, with a clear boundary, the event horizon, that determines what gets trapped and what remains safe. In short, black holes are fascinating, dangerous, and complex, but they don't roam the universe sucking up stars or planets at random. The giant vacuum cleaner myth is just that, a myth. Science shows us that black holes follow the rules of gravity just like any other object, albeit pushed to extreme limits. Respect the event horizon, and you can orbit safely while witnessing one of the universe's most mind-blowing phenomena. So next time you see a science fiction movie with a spaceship being swallowed whole, just remember, black holes are not universe-devouring monsters. They're incredible cosmic objects with boundaries, physics, and rules. Cross those rules, and yes, you're doomed. Stay outside, and you get the best seat in the universe to watch the show unfold. That's science, and it's way cooler than Hollywood.
Wormholes are real shortcuts. If you've ever watched a sci-fi movie, read a space comic, or daydreamed about interstellar travel, you've probably seen this. A spaceship zooms into a glowing tunnel, wobbles a bit, and bam! Suddenly, it's light years away. Stars whip past, time seems to distort, and the ship exits in a completely different galaxy. Welcome to the world of wormholes, the ultimate cosmic shortcut. Or, at least, that's what pop culture would have you believe. Movies, TV shows, and books love wormholes because they solve a huge problem. The universe is enormously big. Light years stretch across empty space, making interstellar travel seem impossible. Wormholes offer a neat, dramatic solution. Fold space-time like a piece of paper, poke a hole, and suddenly the distance between 2 points shrinks to almost nothing. Instant travel. Easy plot device, instant awe factor, and a way to avoid decades or centuries of boring spaceship travel. Who wouldn't want that? But here's the reality check. Wormholes are purely theoretical. They've never been observed, never measured, and we have no evidence that they actually exist anywhere in the universe. The idea comes from Einstein's general relativity equations, which describe how mass and energy warp space-time. Mathematicians noticed that, theoretically, space-time could form bridges between distant points. That's the wormhole idea in a nutshell. A tunnel connecting 2 separate locations in space and time. Sounds amazing, but it's still a concept, a mathematical possibility, not a physical reality. Think of space-time like a flat sheet of paper. Normally, if you want to go from point A to point B, you travel across the surface. Long journey. But if you fold the paper and poke a hole through it, you've created a shortcut. That's your wormhole. Mathematically, it's elegant, visually appealing, and conceptually brilliant. But unlike paper, space-time isn't something we can poke holes into. Or at least we haven't figured out how. Even if wormholes exist, there are huge problems.
For one, they might be inherently unstable. Without some exotic ingredient called negative energy to hold them open, a wormhole would collapse the instant you try to enter it. Imagine stepping into a tunnel that vanishes behind you before you even reach the middle. That's a very real possibility according to the equations. So even if one exists, traveling safely through it could be impossible. Wormholes also raise mind-bending questions about time travel. Theoretically, they might allow you to move not just through space, but through time itself. Enter one end today, exit the other end yesterday. Sounds like sci-fi gold, right? But these are purely speculative scenarios. No one has tested them. No one has observed a real wormhole or used it to jump across the universe. It's all math, imagination, and theoretical physics. This is why wormholes have captured our collective imagination. They're a cosmic cheat code, a what-if scenario that makes interstellar travel possible without waiting thousands of years for light to carry you from one star to another. They let us dream big, question the limits of physics, and imagine adventures that would be impossible under the ordinary rules of the universe. And honestly, that's part of their appeal. Wormholes are the ultimate science fiction turned science possibility, even if it's not something we can actually use. Yet. Here's a fun mental image. Imagine you're an interstellar traveler stuck in traffic. A wormhole opens up, a glowing tunnel appears above the road, and you zip to your destination in seconds. Now swap your spaceship for a car, the cosmic highway for the Milky Way, and that's how wormholes feel in fiction. It's thrilling, awe-inspiring, and impossible to ignore. But the harsh truth is that there's no tunnel yet, no shortcut. The nearest star is still 4.2 light-years away, and unless someone discovers or creates a stable wormhole, that distance is unavoidable. Despite this, wormholes are more than just entertainment. They're a fascinating concept in theoretical physics. Scientists study them to understand the limits of general relativity, quantum mechanics, and space-time itself. They help us explore questions like, could the universe be connected in ways we can't see? Could distant regions interact faster than light would normally allow? Even if we never travel through one, thinking about wormholes stretches our minds and pushes the boundaries of what we consider possible. And here's a fun thought. Even though no wormhole has been observed, physicists don't completely rule them out. The universe is enormous and mysterious. There could be natural wormholes somewhere hidden from view, or maybe future technology could engineer one artificially. It's speculative, but speculation drives science. Every time we imagine wormholes, we're practicing the kind of thinking that has led to discoveries before humans even dreamed they were possible. So what's the takeaway? Wormholes are mind-bending, theoretical shortcuts that capture our imagination, appear constantly in science fiction, and stretch our understanding of the universe. But for now, they remain purely hypothetical. No one has seen one, no one has traveled through one, and unless future physics surprises us, we're stuck with the ordinary, long, and sometimes tedious journey across space. In the end, wormholes are testament to human imagination and the power of theoretical physics. They let us dream about zipping across galaxies, bending time, and skipping light years in seconds. They're exciting, mysterious, and totally mind-boggling. But unfortunately, they aren't real shortcuts, at least not yet. For now, we have to be patient, travel at normal speeds, and keep looking to the stars with wonder, curiosity, and hope that one day, maybe just maybe, science will turn fiction into reality.
You'd be stretched like spaghetti near black holes. If you've ever heard the term spaghettification, your mind probably jumped straight to this. You fall into a black hole, and suddenly your body stretches into a long, thin noodle, like cosmic pasta. Gross, terrifying,
and oddly delicious sounding all at once, right? But here's the catch. Spaghettification doesn't work the same way for all black holes. The universe is a bit more nuanced than that. First, let's explain why this myth exists. Movies, TV shows, and even some popular science articles love to depict people or spaceships being instantly shredded as they approach a black hole. It's dramatic, visually intense, and makes a perfect metaphor for extreme gravity. Stretching into spaghetti is memorable, terrifying, and easy to understand, so it sticks in everyone's mind. But real physics has some interesting twists that most pop culture misses. Spaghettification comes from the idea of tidal forces, which are the differences in gravity experienced over an object's length. Gravity isn't uniform. It's stronger, closer to a massive object. If you were falling feet first into a small black hole, the gravitational pull on your feet would be much stronger than at your head. This difference would stretch you lengthwise while compressing you sideways, creating that long, noodle-like effect. That's where the fun term spaghettification comes from. Scientists actually use it as a real concept in general relativity. Now here's the part that surprises a lot of people. Not all black holes are created equal. Small black holes, maybe a few times the mass of the sun, are ruthless. Their gravity changes very quickly over short distances, so the tidal forces near their event horizon are extreme. Step in, and the stretching happens rapidly. Instant cosmic noodle. Your head, your torso, your legs, everything would elongate fast, and there's no coming back. Small black holes are the true spaghetti chefs of the universe. But the story is different for supermassive black holes, like the one at the center of our galaxy. These beasts are millions or even billions of times the mass of the sun. You might think that makes them even more dangerous, but here's the twist. The tidal forces near their event horizon are actually weaker because the gradient of gravity, the rate at which it changes over distance, is much gentler. If you fell toward a supermassive black hole, you'd still be pulled toward the center, but the stretching would happen slowly. You could theoretically cross the event horizon without feeling extreme stretching immediately. In other words, supermassive black holes are more like slow-motion noodle machines rather than instant shredders. Let's make a mental picture. Imagine standing at the edge of a small black hole. It's like your toes are grabbed by a cosmic claw while your head is yanked in the opposite direction. Instant noodle transformation. Now imagine a supermassive black hole. The pull is still strong, but it's more like leaning on a trampoline very slowly. The stretching is gradual, and you might not notice it right away. The size of the black hole makes a huge difference in how spaghettification actually feels. Astronomers have even suggested that supermassive black holes can swallow stars whole without immediately shredding them. The stars would be pulled in, stretched slightly, and then absorbed. Still terrifying, but nowhere near the instant noodle catastrophe that small black holes produce. It's a fascinating reminder that the universe doesn't always behave the way our imagination or Hollywood expects. And while spaghettification sounds like a gruesome pasta-making process, it's actually a beautiful demonstration of physics in action. The stretching and squeezing follow precise rules dictated by Einstein's general relativity. Gravity isn't just a pull. It's a force that varies over distance and interacts with space-time itself. Spaghettification is like a cosmic demonstration of how extreme gravity can warp not only objects, but the very fabric of space and time around them. Of course, this brings up an important point. You definitely don't want to test this firsthand. Falling into a black hole isn't a thrilling ride. It's a guaranteed fatal encounter. But understanding spaghettification
helps scientists predict what happens to stars and matter near black holes, how jets of energy are formed, and even how black holes grow over time. The phenomenon is central to black hole physics, and it's one of the most dramatic ways to visualize extreme gravity. Here's a little humor for perspective. If you ever plan a black hole adventure, pick a supermassive one. At least you'll get a slow-motion noodle experience rather than instant spaghetti. Small black holes are merciless. Instant pasta, no seasoning required. Either way, it's not a vacation destination, but it is one of the coolest physics concepts in the universe. In short, spaghettification is real, but it's not a one-size-fits-all scenario. Small black holes are ruthless noodle machines, stretching objects violently over tiny distances. Supermassive ones, in contrast, are more forgiving, stretching objects gradually as you cross the event horizon. Either way, it's a mind-bending demonstration of gravity at its most intense, and a vivid reminder of just how strange the universe can be. So, next time someone jokes about being stretched into spaghetti by a black hole, you can smile and say, yes, it's true, but it depends entirely on the size of the black hole. Physics is picky that way. Gravity has rules, tidal forces have limits, and the universe has a wicked sense of humor. The dramatic scenes you see in movies, they exaggerate for effect. Real black holes are even more fascinating, nuanced, and, let's face it, terrifying in a slow-motion, cosmic kind of way. Spaghettification isn't just a quirky term. It's a real, measurable consequence of extreme gravity. And understanding it helps us appreciate the delicate balance of forces in the universe, the mind-bending predictions of general relativity, and why black holes are among the most incredible objects out there. So remember, small black holes are ruthless pasta machines. Supermassive ones are slow-motion noodle experiences. And gravity, well, gravity always gets the last laugh.
Dark matter isn't a substance we can see. If you've ever heard the term dark matter, your mind might have jumped straight to this image. A glowing, mysterious substance floating through space, maybe swirling around stars, planets, or even galaxies, like some cosmic mist. Movies, documentaries, and science shows often make it sound like it's something we can spot, maybe with a high-powered telescope or a special camera. But here's the reality. Dark matter is completely invisible, and that's both what makes it fascinating and what confuses people. First, let's talk about why this misconception exists. The word matter makes it sound like something tangible, something you could touch, see, or at least photograph. And dark just adds a mysterious vibe, right? Combine the two, and it's no wonder people imagine dark matter as some kind of glowing, eerie space substance. It's simple to picture and makes for a great sci-fi story. But the truth is far more subtle and way more mind-blowing. Dark matter doesn't emit light, reflect it, or interact with normal matter in ways we can directly detect. You can't point a telescope at a patch of sky and see it twinkling. You can't collect a sample and study it in a lab. Dark matter is invisible. Completely. Nada. Zilch. The only reason scientists even know it exists is because of the gravitational effects it has on objects we can see, like stars, galaxies, and clusters of galaxies. Imagine this. You're at a crowded dance floor. People are moving around, bumping into invisible bumpers, and you can't see the bumpers themselves. You only notice them because they affect how the dancers move. That's dark matter. You can't see it but you can measure its presence by observing the bumps it creates in the motion of stars and galaxies. It's like a cosmic ghost, unseen, mysterious, but undeniably real because of the traces it leaves behind. One of the first clues came when astronomers looked at galaxies and noticed something weird. Stars at the edges of galaxies were moving too fast, so fast that without some extra mass holding them together, the galaxies should have flown apart. There wasn't enough visible matter to account for this. Enter dark matter, the invisible glue keeping galaxies intact, the cosmic scaffolding holding the universe together. Without it, galaxies would literally fly apart. Here's another fun way to visualize it. Picture spinning a merry-go-round. If you put a little weight at the edges, it spins fine. But imagine there's far more weight than you can see, hidden weights inside that you can't detect, yet they change how fast the ride spins. That's essentially what dark matter does. Invisible, but powerful. It affects the motion of everything we can see, shaping galaxies and clusters in ways ordinary matter alone can't explain. And let's put it in perspective. Dark matter makes up about 27% of the universe. Compare that to the 5% of the universe made of normal matter, the stars, planets, gas, dust, and humans. The remaining 68%? Dark energy, another cosmic mystery. That means the vast majority of the universe is invisible, mysterious, and something we can't touch or see directly. We live in a universe where most of what exists is hidden from our eyes. That's both terrifying and amazing at the same time. Physicists are actively trying to figure out what dark matter actually is. It could be made of exotic particles that barely interact with normal matter. Or it might be something completely different, something we haven't even imagined yet. Detecting dark matter directly is one of the most ambitious challenges in modern physics. Scientists have built massive underground detectors, launched satellites, and even created particle colliders in hopes of catching a hint of it. So far, still invisible, still mysterious, and still shaping galaxies silently in the background. Here's a mind-bending thought. The reason we even know dark matter exists is because the universe gives it away through gravity. That means it has mass, it pulls on things, and it bends light. That last one, light bending, is called gravitational lensing, and it's one of the coolest tricks astronomers use to see dark matter. Light from distant galaxies bends as it passes through areas with lots of dark matter, creating arcs, rings, and distorted images. You can't see the dark matter itself, but you can see its fingerprints in the light around it. It's like watching footprints in the sand and deducing that someone walked by, even if you never saw the person. Casually thinking about it, dark matter is kind of like a cosmic puppet master. It moves stars, bends light, shapes galaxies, and orchestrates the universe, all while remaining completely unseen. It's mysterious, it's invisible, and it's essential for the structure of the cosmos. Without it, galaxies would fall apart, stars would drift away, and the universe would look very different. So the next time someone says, "Oh, dark matter, we can see it," smile and nod, but know the truth. Dark matter is invisible, completely intangible, and detectable only through its effects on visible matter. It's the silent architect of the universe, the unseen hand guiding the dance of galaxies, and one of the biggest mysteries we've yet to solve. And that's what makes it so exciting. It's the ultimate cosmic game of hide and seek,
and scientists are determined to find it, even if it refuses to show itself directly.
In short, dark matter is not a glowing, spooky substance floating in space. It's invisible, elusive, and only inferred by the traces it leaves on the universe. It makes up a huge chunk of everything out there, shapes galaxies, bends light, and remains one of the most fascinating puzzles in modern physics. It's the hidden backbone of the cosmos, silently controlling the structure of everything we can see, and a reminder that the universe is far more mysterious than it appears.
Dark energy is just empty space. If you've ever looked up at the night sky and thought about space, you might imagine it as, well, mostly empty. A big, dark void sprinkled with stars, planets, and galaxies. Easy to picture, right? Empty, quiet, vast. Some people even call it nothing. But here's the cosmic twist. That nothing isn't nothing at all. In fact, scientists discovered that this empty space is filled with something incredibly powerful and mysterious called dark energy. And it's doing something wild. It's accelerating the expansion of the universe. Now, you might be thinking, wait, if dark energy is everywhere, why haven't we seen it? Where is it? That's the thing. It's invisible. You can't see it, touch it, or directly measure it with a telescope. It doesn't emit light, it doesn't block light, and it doesn't interact with matter in ways we can detect easily. But here's the kicker. We know it exists because of what it does, not because we can see it. It's a bit like wind. You can't see it, but you can feel it. See trees sway or watch flags flap in its presence. Dark energy is like the wind of the cosmos, pushing galaxies apart faster and faster over time. The story of dark energy is actually fairly recent in science. Back in the late 1990s, astronomers were studying distant exploding stars called supernovae to measure how fast the universe was expanding. They expected the expansion to be slowing down, thanks to gravity pulling everything together. But the data was shocking. The expansion wasn't slowing, it was speeding up. Galaxies were racing away from each other faster than ever before. Scientists realized something invisible, mysterious, and incredibly powerful must be causing this, and thus dark energy entered the cosmic stage. So no, dark energy isn't just empty space. It's a force or property of space itself that dominates the universe. It makes up about 68% of everything out there. Compare that to the 27% that is dark matter, another mysterious, invisible thing, and the 5% that is all the normal matter, planets, stars, gas, humans. You get the idea. Most of the universe is invisible, intangible, and almost completely unknown. That's a little humbling, isn't it? The vast majority of what exists in the cosmos is something we can't see directly. How can we picture it? Well, imagine a balloon. You draw tiny dots on the surface of the balloon to represent galaxies. Now start inflating the balloon. As the balloon expands, the dots move away from each other. That's normal cosmic expansion. But dark energy is like having an invisible hand pushing on the balloon, stretching it faster and faster. You don't see the hand, but the effect is obvious.
Galaxies accelerate away from each other, and the universe keeps getting bigger at an increasing rate. It's invisible, yes, but incredibly real. And here's something fascinating. Unlike gravity, which pulls things together, dark energy pushes things apart. It's the cosmic anti-gravity force, quietly dominating the fate of the universe. Without dark energy, the universe's expansion might be slowing down, and the distant future of galaxies, stars, and planets could be very different. With it, the cosmos is on a trajectory that's still mysterious but undeniably accelerating. Despite being so dominant, scientists still don't know what dark energy really is. Some theories suggest it's a property of space itself, a kind of energy that exists simply because space exists. Others propose it's a new kind of field or particle we haven't discovered yet, and there are plenty of wild speculative ideas too. But here's the thing. Even without knowing exactly what it is, we can measure its effects. Dark energy is like noticing someone rearranging your room while you weren't looking. You don't see them, but you notice things moving and shifting in ways that can't be explained otherwise. Thinking about dark energy casually can be mind-blowing. That empty-looking space between galaxies isn't empty at all. It's filled with something that controls the expansion of the universe, shapes galaxies, and dominates the fate of everything we see. Most of the universe is not made of stars, planets, or even visible matter. It's made of this invisible, mysterious force. And the best part? We're still figuring it out. Every new observation, every new telescope, every new experiment could bring us closer to understanding what dark energy actually is. So the next time someone says space is empty, you can smile and tell them, actually, empty space is incredibly powerful. It's controlling the expansion of the entire universe. That's not just trivia, it's one of the most profound revelations in modern astrophysics. Empty space isn't nothing, it's something stranger, invisible, and massively important. In short, dark energy isn't a void, a vacuum, or nothing in the usual sense. It's a mysterious, invisible force driving the accelerated expansion of the universe. It shapes galaxies, dominates the cosmic budget, and continues to puzzle scientists around the world. The universe is bigger, stranger, and far more mysterious than our everyday experience suggests. And dark energy is a perfect example of that. It reminds us that just because we can't see something, it doesn't mean it isn't there, or that it isn't shaping everything around us in ways we are only beginning to understand.
We've seen the edge of the universe. Have you ever heard someone say, "We've seen the edge of the universe"? Maybe in a documentary or an article. They made it sound like astronomers have peered off a cosmic cliff and glimpsed the limits of everything that exists. Epic, right? A literal edge of reality. Well, not quite. The truth is far more mind-bending and mysterious than that. Let's break it down. When people say we've seen the edge of the universe, what they really mean is the observable universe. That's the portion of the cosmos where light has had time to reach us since the Big Bang, which happened about 13.8 billion years ago. Because the universe is expanding, that distance is actually around 46 billion light-years in every direction. So we can see incredibly far, but there's still a limit. Beyond that horizon, we have no information. No matter, no light, nothing. It's easy to understand why this gets confusing.
The Hubble Space Telescope, James Webb Space Telescope, and other observatories have given us jaw-dropping images of galaxies billions of light-years away. The detail is so stunning that it feels like we're standing right next to them. And when astronomers call a picture a deep field, it sounds like we're literally looking at the edge. Pop culture reinforces this idea too. Space is portrayed as having definite boundaries. But in reality, the universe doesn't necessarily have an edge in the way a room has walls. Here's a mental image. Imagine standing in a foggy field. You can see trees and grass up to a certain distance, but beyond that, everything is hidden in mist. You know the field continues, but you just can't see it yet. That's exactly how the observable universe works. The fog is the limit of light travel. Anything beyond it hasn't had time to reach us. The rest of the universe could be unimaginably vast, infinitely stretching, or even different in structure, but we simply have no way of observing it. The observable universe alone is astonishing. It contains around 2 trillion galaxies, each with billions of stars, planets, and probably countless unknown wonders. And that's just what we can see. Beyond that, who knows? There could be more galaxies, enormous voids, or cosmic phenomena that defy our imagination. Some theories even suggest the universe could be infinite. If so, the concept of an edge might be meaningless. There might not even be an edge in the traditional sense. Even with our most powerful telescopes, we're limited. Light from regions beyond the cosmic light horizon hasn't reached us yet, and because the universe is expanding, some distant regions will never be observable. The expansion stretches the space between galaxies faster than light can travel across it, which means there are parts of the cosmos we may never see. This creates a humbling perspective. What we know is only a tiny fraction of what exists. The rest remains a mystery. Here's a fun way to imagine it. Picture your favorite video game with a fog of war mechanic. You can see only the areas your character has explored. The rest is hidden until you move closer. The observable universe is like the part of the map that's been revealed. The unexplored regions are beyond our sight, and who knows what weird or amazing things could be there. New galaxies, strange cosmic structures, entire physics we haven't yet discovered. That's the excitement of astronomy. The known is just the beginning. Now, some people ask, if we can't see it, how do we know the universe goes beyond the observable part? Good question. We infer it from several observations. The universe appears homogeneous and isotropic on large scales, meaning it looks roughly the same in every direction. This suggests that space continues beyond what we can observe, even if we can't confirm it directly. It's like assuming that the foggy field continues, because the part you can see stretches on without interruption. So when someone tells you, "We've seen the edge of the universe," here's the reality check. What we see is just the slice of the observable universe. There might not be a true edge at all. What lies beyond could be more galaxies, more stars, or something we haven't even imagined yet. The universe, in many ways, is far bigger and stranger than our minds can comprehend. And that's what makes it so exciting. Every new telescope, every new observation pushes the horizon of what we can see a little further, revealing more of the cosmic landscape. The observable universe is already enormous, but it's only the tip of the cosmic iceberg. Beyond it lies the truly unknown, a region that may never be fully explored. This gives astronomy a magical quality. It's a science built on observation, mathematics, and imagination, where most of the universe is invisible, mysterious, and waiting for us to understand it. Next time someone casually says, "We've seen the edge of the universe," you can smile knowingly and say, "Nope, we've seen a tiny slice of it, and the rest, still a cosmic mystery." That's the beauty of astronomy. Even with all our incredible instruments and observations, the universe keeps secrets, and the true scope of it may forever lie beyond our reach. In short, the universe doesn't have a clear edge like a tabletop or a wall. Only what we know is the observable universe, limited by how far light has traveled since the Big Bang. Beyond that, space could stretch infinitely, or have structures and phenomena entirely different from what we know. The rest remains unknown, untouched, and profoundly mysterious, a humbling reminder that the cosmos is far bigger than anything we've explored. And that, in itself, is breathtaking.
The sky is black because space is dark. Have you ever looked up at the night sky and thought, space is so black, why isn't it glowing with all that sunlight? It's one of those things that seems obvious at first glance. I mean, the sun is out there, shining billions of kilometers away, and yet the sky is pitch black. Movies, cartoons, and even casual conversation make it seem like space is just naturally dark. But the truth? Physics is behind that black canvas, and it's actually pretty fascinating. Most people assume space is black because, well, there's nothing out there. No air, no clouds, no light. Makes sense, right? If there's nothing to reflect or scatter light, it should be dark, and that's partly true. But the real reason is a little more specific. It's because there's no atmosphere to scatter sunlight. On Earth, our sky is blue, not because blue light is inherently everywhere, but because sunlight interacts with air molecules in the atmosphere. This process, called Rayleigh scattering, bends and spreads shorter wavelengths of light like blue across the sky, filling it with color. That's why even when the sun is high up, the entire sky appears blue. Now imagine removing the atmosphere completely. No air molecules, no clouds, no light. That's basically what space is. The sun still shines, stars still emit light, but there's nothing to spread the light around. So unless you're looking directly at a light source, your eye just sees darkness. That's why astronauts in orbit or on the moon report seeing the sun as blindingly bright. But the surrounding sky is completely black. The stars stand out like diamonds on black velvet because there's no background scattering to dull their shine. Here's a mental image. Picture yourself floating in a vacuum chamber. A tiny flashlight is pointed at you, but the chamber is completely empty. The flashlight illuminates the spot it hits, but the rest of the room remains dark because there's nothing to diffuse the light. Space works similarly. The sun is the flashlight, the vacuum of space is the chamber, and the stars are little pinpricks of light shining through the darkness. The result is this striking, high-contrast view that looks surreal compared to our daytime sky on Earth. It's also why photographs from space looked so dramatic. Images taken from the International Space Station or the Hubble Space Telescope show the sun, planets, and stars in vivid clarity against a pure black background. No haze, no clouds, no atmosphere to soften the view. In some ways, the universe is showing off its minimalist high-definition style. Fun fact,
Even astronauts experience this effect directly. During a spacewalk, if you turn away from the sun, the blackness can be intense, utterly dark, like staring into the void. And if you look at the stars from orbit, they don't twinkle the way we see them on Earth. Twinkling is caused by our atmosphere bending starlight. Without it, the stars shine steadily, crisp and clear against the black backdrop. Space is not just dark, it's deeply, starkly, beautifully black, with stars appearing more brilliant than anything we can experience on the ground. Interestingly, this also explains why sunrise and sunset look so spectacular on Earth. As sunlight passes through the atmosphere at an angle, the scattering effect changes. Short wavelengths like blue scatter out, leaving reds and oranges to dominate the horizon. In space, you don't get that. Sunrises and sunsets don't glow across the sky. They're just sudden changes in light against a pitch-black background. The effect is much more dramatic and stark than anything we experience on Earth. So next time someone casually says, "The sky is black because space is dark," you can smile knowingly and explain, it's not darkness that makes it black. It's the absence of atmosphere to scatter light. Space is filled with light sources, but the vast vacuum of emptiness ensures that, except where the light shines directly, your eyes perceive absolute blackness. In a way, the universe is giving stars the perfect stage, allowing them to shine brilliantly against an infinite dark canvas. Even though it may seem counterintuitive at first, it makes perfect sense. Once you understand the physics, the color of the sky isn't just about light being present or absent. It's about how light interacts with matter. On Earth, our atmosphere takes sunlight and spreads it across the sky, giving us the familiar blue we see during the day. In space, no such scattering occurs, and the natural result is darkness. That's why astronauts describe space as both breathtakingly beautiful and eerily black. The sun shines like a spotlight, planets gleam, and stars sparkle, all against a backdrop so black it's almost impossible to imagine. In short, the blackness of space isn't because the universe is naturally dark. It's because there's no atmosphere to scatter light. Light is out there, more abundant than we can imagine, but it travels in straight lines through the vacuum until it reaches an object or our eyes. The result is a sky that's black, striking, and infinitely mysterious, providing the perfect contrast for the dazzling lights of the cosmos.
Comets are fiery balls. When most people think of a comet, they imagine a blazing fireball streaking dramatically across the night sky, like some cosmic torch racing through space. Movies, cartoons, and even old textbooks love to show comets as flaming balls zooming across the heavens. It's a spectacular image, and kind of makes you feel like if a comet got too close, it would burn everything in its path. But here's the truth. Comets are not fiery, not even close. In fact, they're more like cosmic snowballs with a personality. So why do so many people think comets are on fire? Well, it's easy to see why. Comets have those long, bright tails that glow brilliantly in the night sky. They appear to shoot across the sky at high speed. When captured in photographs, the tail can look like flames streaming behind the comet. It's very cinematic. So, naturally, the human brain makes the leap. Glowing tail equals fire. And if it glows, it must be hot, right? Not exactly. Let's break it down. A comet is mostly ice, dust, and frozen gases. These are ancient leftovers from the formation of the solar system, kind of like the original recipe for planets, preserved in frozen form for billions of years. A comet's nucleus, the core, is usually only a few kilometers across, tiny compared to planets, and extremely cold, sometimes reaching temperatures as low as -200 degrees Celsius. So the idea of a fiery, burning comet, completely wrong. The comet itself is frozen solid, not a fireball. The bright, dramatic tail, that's where the misunderstanding comes from. When a comet approaches the sunlight warms it up. This causes ice to sublimate. Basically, it turns directly from solid to gas. Dust particles trapped in the ice are released into space. This combination of gas and dust forms a glowing cloud around the comet, called a coma, which can be tens of thousands of kilometers wide. Then, solar radiation and the solar wind, the stream of charged particles flowing from the sun, push this material away from the comet, creating the famous comet tail that we see from Earth. Here's a way to picture it. Imagine a dirty snowball flying past a heat lamp. As the snowball warms, ice melts and dust drifts away, forming a faint glowing trail behind it. That's essentially what a comet does near the sun. No fire, no explosion, just sublimating ice and drifting dust forming a stunning tail. And the best part? The tail doesn't necessarily trail behind the comet in the direction it's moving. It always points away from the sun because that's the direction the solar wind is blowing. So a comet can move in one direction while its tail streams in another, which can look magical or even confusing to observers on Earth. Comets also vary in appearance. Some have short, stubby tails. Others display long, magnificent tails stretching millions of kilometers. Some comets even develop multiple tails, one of gas, one of dust, each shaped differently by the sun's energy and the solar wind. That's why each comet passing near Earth can look completely unique, almost like a signature cosmic brushstroke. Astronomers have been fascinated by these icy travelers for centuries. Take Halley's Comet, for example. It pops into view roughly every 76 years, carrying a pristine sample of the early solar system along with it. Every time it swings by, it reminds us that these icy wanderers are ancient messengers from the dawn of our cosmic neighborhood. It's also worth noting that comets aren't just beautiful, they're scientifically valuable. The material in comets contains primordial ices and organic compounds, which could provide clues about how the solar system formed, and even how life-essential chemicals arrived on Earth. So the next time you see a comet streak across the sky, think of it as a frozen time capsule, not a blazing inferno. And here's a fun little thought. When you hear someone say, "That comet is on fire," you can nod politely and explain, "Sure, if you like fiery snowballs streaking through space, the reality is way cooler and colder than the fiery myth." Comets are icy, dusty travelers with tails shaped by sunlight and solar wind, not fire. Their beauty comes from subtle physics and cosmic mechanics, not literal flames. In short, comets are mostly ice and dust, with their spectacular tails formed by sunlight pushing gas and dust away. They're not burning, they're not exploding, and they're not dangerous fireballs. They're ancient, frozen remnants of the solar system, gracefully streaking through space and giving us one of the most mesmerizing natural light shows imaginable. Next time you see a comet in the night sky, remember, what looks like fire is actually sunlight sculpting ice and dust into a glowing cosmic masterpiece. It's a reminder that space can be far stranger and more beautiful than our fiery assumptions suggest.
Shooting stars are stars. We've all seen them. Those brilliant streaks of light racing across the night sky, prompting instant wishes and awe. Maybe you were camping, lying on your back, counting shooting stars with friends. Or maybe you were stuck in a city, glancing up and saw a sudden flash, thinking, "Wow, a shooting star!" For generations, humans have called them shooting stars, and it's easy to see why. They flash bright, move quickly, and for a brief moment dominate the sky like tiny stars on the run. But here's the twist. They aren't stars at all, not even close. The name is a complete misnomer. In reality, shooting stars are tiny bits of rock or dust, meteoroids, hurtling through space at incredible speeds. And when they meet Earth's atmosphere, they ignite. That streak of light? It's the meteoroid burning up from friction with air as it crashes through the sky. Think about it. A star is a massive nuclear-powered sun billions of kilometers away. Shooting stars? They're usually smaller than a pebble. They don't produce energy themselves. They only shine because they're burning up due to extreme heat generated by moving through our atmosphere at tens of kilometers per second. The speed is mind-boggling. Imagine a baseball flying faster than a commercial jet, then hitting air so thick that it instantly makes the rock glow. That's what happens when meteoroids become shooting stars. The science behind it is fascinating. When a meteoroid enters Earth's atmosphere, it encounters air molecules at an incredibly high velocity. This causes compression and friction on its surface, which rapidly heats the rock, vaporizing part of it and creating a glowing trail called a meteor. The trail is what we see from the ground, a brilliant streak of light that often lasts just a second or two. Sometimes the meteor brightens dramatically if the meteoroid is large, creating what astronomers call a fireball. These rare events can outshine even the moon for a brief moment. Here's a mental image. Picture tossing a tiny rock into a blazing furnace while it's spinning at insane speed. Sparks fly, the rock glows red hot, and then it disintegrates into dust. That's essentially what a shooting star is, nature's own cosmic fireworks display. But unlike fireworks on Earth, this spectacle is entirely natural and happens continuously above our heads, even when we don't notice. Now, most meteoroids are tiny, often smaller than a grain of sand. That means almost all of them burn up completely in the atmosphere. That's why we rarely find meteorites, the surviving fragments that make it to the ground. When you see a shooting star streaking across the sky, you're witnessing something incredibly fleeting, a tiny rock from space being destroyed in a fiery display, often before it ever has a chance to touch Earth. Meteor showers are another spectacular aspect of these cosmic visitors. Events like the Perseids in August or the Geminids in December occur when Earth passes through debris left behind by comets. Each tiny fragment enters our atmosphere at high speed, creating dozens or hundreds of shooting stars in a single night. It's like walking through a cosmic sprinkling of glitter, where every speck lights up the sky for a fraction of a second.
These showers are a reminder that our planet is not isolated. It's constantly moving through a sea of space debris left over from the solar system's formation. Astronomers have been fascinated by meteors for centuries. Ancient civilizations even interpreted them as omens or messages from the gods. Today, we understand them as natural phenomenon, and in some cases, sources of valuable information about the early solar system. Meteorites contain materials that predate Earth itself, giving scientists clues about the building blocks of planets and even life. So, in a way, every shooting star you see is not just beautiful, it's a tiny messenger from the cosmos, telling a story billions of years in the making. It's also fun to note the cultural impact. Shooting stars have inspired countless wishes, legends, and poems. The idea that a fleeting streak of light could carry your wish into the universe is magical, even if it's technically just a meteoroid burning up. Science doesn't ruin the magic here, it enhances it. You get to appreciate that what seems like a simple streak of light is actually a tiny blazing traveler from outer space performing a one-time-only light show in Earth's atmosphere. So, next time someone points at the sky and says, "Look, a shooting star," you can smile knowingly and explain, "Not a star at all. It's a meteoroid burning up in the atmosphere." But don't ruin the fun. Make a wish anyway. The science behind it doesn't take away the awe, it makes it even more incredible. You're watching a rock from billions of kilometers away, traveling at insane speed, igniting in a fiery trail for a split second. That's a cosmic spectacle most of us will never get to touch, yet we can admire it safely from Earth. In short, shooting stars aren't stars. They're meteoroids entering Earth's atmosphere, burning up due to friction, and creating the fleeting streaks of light we love to watch. Tiny, fast, and spectacular, they remind us that even small rocks from space can light up our skies and our imaginations. Next time you see one, remember, it's not a distant sun racing across the sky. It's a cosmic pebble putting on a fiery show, all thanks to physics, speed, and the magic of Earth's atmosphere.
All planets orbit perfectly circular. When most of us imagine the solar system, we picture planets gliding around the sun in neat, perfect circles. Maybe you've seen animations where Earth, Mars, and Jupiter trace flawless loops like balls on a cosmic racetrack. It looks tidy, orderly, almost hypnotically predictable, and honestly, it's a satisfying picture. Perfect circles make sense to our human brains. They're easy to draw, easy to animate, and easy to understand. But here's the cosmic reality check. Planets don't orbit in perfect circles. Not even close. The truth is that most planetary orbits are elliptical, which basically means they're stretched out ovals rather than perfect circles. Some ellipses are only slightly stretched, almost circle-like, while others are dramatically elongated. Earth's orbit is relatively circular, which is why our seasons and distances from the sun seem so stable. But even Earth isn't a perfect circle. It's just close enough that we don't notice a huge difference day to day. Other planets tell a more dramatic story. Mercury, for example, has an orbit that's noticeably more oval-shaped than Earth's. That means its distance from the sun changes significantly over the course of a single orbit. When it's closest to the sun, what astronomers call perihelion, it's moving faster, pulled in by the sun's stronger gravity. When it's farthest away, aphelion, it slows down. This speeding up and slowing down isn't random. It's a natural consequence of moving along an ellipse. You can imagine it like this.
Picture a rubber band stretched around a circle. If you squish it slightly on one side, it becomes an oval. And a planet moving along that oval doesn't move at a uniform speed. It zips along faster on the squeezed side and eases up on the stretched out side. Gravity is constantly tugging and adjusting its motion, making the orbit dynamic and exciting, rather than a boring, uniform loop. And Earth isn't the only one with a subtle ellipse. Pluto, now classified as a dwarf planet, has a famously elongated orbit. Its path swings it from inside Neptune's orbit to way out past the other outer planets. So sometimes it's closer to the Sun than Neptune, and other times it's far beyond even the outer reaches of our planetary neighborhood. Its orbit is dramatically stretched, showing just how varied planetary paths can be. Elliptical orbits aren't just limited to our solar system. Observations of exoplanets, planets orbiting other stars, reveal some wildly eccentric paths. Some exoplanets whip extremely close to their stars and then swing far out into space, taking years to complete a single orbit. Others move in nearly perfect circles. The universe is full of variety, and circular orbits are actually the exception rather than the rule. This understanding of planetary motion came to us thanks to Johannes Kepler, a brilliant astronomer from the early 1600s. Before Kepler, people thought planets traveled in perfect circles, following the tradition of Aristotle and Ptolemaios. Kepler analyzed detailed observations of Mars made by Tycho Brahe and realized that the data didn't match a circular orbit. After much study, he formulated his first law of planetary motion. Planets move in ellipses with the Sun at one focus. This was a revolutionary idea, completely transforming how humanity understood the cosmos. Kepler's discovery also explained why planets speed up and slow down along their orbits, leading to his second law, which says that a line joining a planet and the Sun sweeps out equal areas in equal times. In simple terms, this means that planets move faster when closer to the Sun and slower when farther away. Perfect circles? Nope. Ellipses with a bit of drama? Absolutely. Why do we care about elliptical orbits? Well, they affect everything from climate to space missions. Earth's slightly elliptical orbit contributes subtly to seasonal variations, though axial tilt is the main driver of seasons. For other planets, eccentric orbits can lead to extreme temperature swings, affecting potential habitability or the behavior of moons. And for astronauts or spacecraft planning missions, understanding these ellipses is crucial for plotting accurate trajectories. A circular orbit assumption could lead to missed rendezvous or dangerous miscalculations. So, the next time someone tells you that planets orbit in perfect circles, you can smile knowingly and say, sure, if you like ignoring gravity and real physics. The universe isn't a tidy classroom diagram. It prefers ellipses, curves, and a little chaos, with planets speeding up and slowing down as they dance around the Sun. Each orbit has personality, shaped by gravity, initial motion, and interactions with other planets. Perfect circles are rare. Ovals, stretched ellipses, and slightly squashed loops dominate the solar system. In short, most planetary orbits are elliptical, some barely different from circles, others wildly stretched. Planets don't glide in flawless loops. They zip, coast, and curve along paths dictated by gravity. Perfect circles, very rare. The universe prefers curves with a little drama, making planetary motion dynamic, unpredictable in subtle ways, and endlessly fascinating. Next time you picture the planets orbiting the Sun, remember, it's not a clean racetrack. It's a cosmic dance in stretched loops and elegant ovals, and every planet is performing its own unique choreography.